Water, the source of life. The world is facing a difficult future, where millions lack access to this essential life element. We urgently need innovative solutions. The United Arab Emirates, as one of the leading countries in tackling water scarcity, reinforces its position as a hub of rain enhancement science to create a better future for the country and the world. Under the patronage of His Highness Sheikh Mansour bin Zayed Al Nahyan, Deputy Prime Minister and Minister of Presidential Affairs, the National Centre of Meteorology, through UAE Research Programme for Rain Enhancement Science, organises the International Rain Enhancement Forum, which brings together leading international and national scientists, researchers and innovators to tackle the world's ever-pressing sustainability and water issues. Building on the success of our previous 4 forums, we welcome you to the 5th International Rain Enhancement Forum, where we are still united for water security.
Ladies and gentlemen, good afternoon. My name is Yusuf Abdul Bari, and I will be the Master of Ceremonies today. It is a great pleasure to welcome you all to the virtual 5th International Rain Enhancement Forum, held under the patronage of His Highness Sheikh Mansour bin Zayed Al Nahyan, Deputy Prime Minister and Minister of Presidential Affairs. This event is organized by the National Centre of Meteorology through the UAE Research Programme for Rain Enhancement Science. Distinguished guests, we are gathered here today to highlight the latest scientific and technological advancements in rain enhancement research. In these 2 days, the program will announce the inauguration of its 4th cycle and will showcase the latest updates from its 9 awardee projects. Furthermore, we will take a close look at the key themes and pillars of rain enhancement and engage in interesting debates on how to better tackle the challenges of global water stress. We are confident that this event will lead us to a broader collaboration towards the development of innovative solutions to tackle water scarcity. We hope that IREF sessions will be enriching and productive for everyone. To begin this promising forum, ladies and gentlemen, I would like to invite His Excellency, Dr. Abdullah Al-Mandous, Director of NCM and President of the Regional Association to Asia of WMO, and on behalf of His Highness Sheikh Mansour bin Zayed Al Nahyan, Deputy Prime Minister and Minister of Presidential Affairs, to deliver the opening remarks of this year's IREF.
السادة الحضور، السلام عليكم ورحمة الله وبركاته. يشرفني أن أرحب بكم وأن ألقي على مسامعكم الكلمة الافتتاحية لسمو الشيخ منصور بن زايد آل نهيان، نائب رئيس مجلس الوزراء وزير شؤون الرئاسة. بسم الله الرحمن الرحيم. السادة العلماء والخبراء والمختصين، الحضور الكرام، السلام عليكم ورحمة الله وبركاته. يشرفني ونحن نفتتح النسخة ال5 من الملتقى الدولي للاستمطار أن أنقل لجمعكم الكريم تحيات صاحب السمو الشيخ خليفة بن زايد آل نهيان رئيس الدولة حفظه الله، ودعمه الكامل لكل ما يعزز الاستدامة المائية على مستوى العالم، وتقديره لما يبذله المجتمع العلمي من جهد بحثا عن حلول علمية لمشكلة شح المياه التي هي قضية أمن قومي وأولوية وطنية ودولية ملحة. وضمن هذا التقدير يأتي اهتمام صاحب السمو رئيس الدولة بهذا الملتقى الذي أصبح منصة عالمية تجمع الباحثين والخبراء والمختصين في بحوث علوم الاستمطار من كل دول العالم. تعد قضية الأمن المائي محورا رئيسا في اهتمام الحكومات على مستوى العالم، لا سيما أن ندرة المياه أصبحت تؤثر على أكثر من 40% من سكان العالم، ووفقا لتقارير الأمم المتحدة من المرجح أن ترتفع هذه النسبة إلى 50% بحلول سنة 2030، مما يتطلب تضافر الجهود البحثية الوطنية والإقليمية والدولية لتشجيع البحث والتطوير والاستثمار في التقنيات الجديدة وإقامة الشراكات الفاعلة. تسعى دولة الإمارات العربية المتحدة وضمن استراتيجيتها الوطنية للأمن المائي إلى ضمان استدامة واستمرارية الوصول إلى المياه خلال الظروف الطبيعية وحالات الطوارئ القصوى. فقد أطلقت الدولة في سنة 2015 برنامج الإمارات لبحوث علوم الاستمطار الذي يهدف إلى زيادة هطول الأمطار وتعزيز إمدادات المياه العذبة داخل الدولة، إلى جانب توفير نتائج علمية قابلة للتطبيق بشكل أوسع في المناطق الجافة وشبه الجافة من العالم، التي تعد من أكثر المناطق شحا في الموارد الطبيعية للمياه. الحضور الكرام، إن قضية المياه هي شأن مشترك للبشرية، ويتطلب منا التعاون من أجل ضمان توفير هذا المورد الأساسي والمهم لمن يحتاجه حول العالم. وضمن هذا الوعي ينعقد هذا الملتقى يشكل منصة جامعة للخبراء والباحثين لمناقشة التحديات وإيجاد الحلول المبتكرة لمعالجتها. ندعو الله أن تكلل جلسات وفعاليات هذا الملتقى الذي ينعقد أول مرة افتراضيا بسبب الظروف التي فرضتها جائحة كورونا، بنتائج وأفكار مبدعة وجديدة يكون لها الأثر المباشر في تطور وتقدم بحوث علوم الاستمطار محليا وعالميا، وبما يدعم المساعي الدولية الرامية إلى الحد من شح المياه. وفقكم الله، والسلام عليكم ورحمة الله وبركاته.
Thank you, Your Excellency, for the inspirational message. Dear guests, let us now walk you to the second part of our opening ceremony with a brief introduction of the UAE Research Program for Rain Enhancement Science as we are launching its fourth cycle. The UAE Research Program for Rain Enhancement Science is an international research initiative designed to promote scientific advancement and the development of new technology in this area. Launched under the patronage of His Highness Sheikh Mansour bin Zayed Al Nahyan, the Deputy Prime Minister and Minister of Presidential Affairs, the program supports the UAE's National Innovation Strategy. The program is managed by the National Center of Meteorology, NCM, as part of its mission to support research in weather modification. It offers a grant of $1.5 million to the winning research proposals, where the program and the center will collaborate with the awardees over a period of 3 years as we aim to tackle water security globally.
$785 million people worldwide don't have access to clean water. For a better world, the UAE has always sought to be a pioneer in all areas of development and research, especially in those that advance environmental sustainability. His Highness Sheikh Mansour bin Zayed Al Nahyan, Deputy Prime Minister and Minister of Presidential Affairs, established the UAE Research Program for Rain Enhancement Science, the first of its kind international research initiative designed to stimulate and promote scientific advancement and the development of new technology in the area of rain enhancement. The program attracted many researchers and scientists from several countries, leading to the submission of hundreds of proposals. With its 9 internationally awarded projects, the program has made a major impact in understanding and implementing the most efficient methods to improve cloud seeding operations and develop state-of-the-art technologies. Building on the success of its previous awardees, the UAE REP's 4th cycle offers a grant of up to $1.5 million for each awarded research proposal with the most innovative ideas. The UAE will continue to work towards having a significant impact on finding new solutions to prevent water scarcity, attain water security, and protect future generations.
Thank you for tuning in. Now let us welcome Mrs. Alia Al-Mazroui, the Director of the UAE Research Program for Rain Enhancement Science, to the virtual stage, as she will provide us with an overview of this year's forum and insights about the launch of UAE REP's 4th cycle.
Assalamu alaikum wa rahmatullahi wa barakatuh. Your Excellencies, esteemed guests, ladies and gentlemen, it's my pleasure to welcome you to the 5th and first virtual International Rain Enhancement Forum. Thank you for joining us. What a year! If any of you had told me last year that I would be giving the 2021 IREF opening remarks virtually because a viral infection had suddenly, silently, and stubbornly made its way into every community on the planet, I would not have believed you. It is no exaggeration to say that the ongoing coronavirus pandemic has disrupted and displaced us, economically, socially, and existentially. Many of our underlying challenges have been exacerbated, especially the inequalities caused by lack of access to water across the globe. During these unprecedented times, our industry has had to adapt, and quickly, because what we do remains crucial towards sustaining water resources for future generations. With this context in mind, the theme for the 5th International Rain Enhancement Forum has never been more appropriate. Now, more than ever, we must be united for water security. United in our mission to bring water to the most arid landscapes. United in our strategies of achieving accessible water for all. United in our commitment to the scientific method that has brought us so far. As we all know, these ambitions cannot be realized overnight. Indeed, given the nature of the work required in this field, the exacting detail and meticulous rigor that is applied to the investigation and experimentation of rain enhancement technologies, IREF will move to a biannual calendar. This 2-year fixture will allow our scientists, researchers, and technologists the time they need to harness emerging technologies and techniques. And once they are equipped with them, they can fully investigate new theses to arrive at comprehensive findings and results with the utmost confidence in their outcomes and empirical methods. Let us remember that our aim here is to foster cooperation, to unlock innovative strategies, to secure and sustain fresh water across the globe. Ladies and gentlemen, turning to this year, at the 5th Forum, we will explore a vast range of innovative technologies and techniques. We will explore how novel nanomaterials, artificially intelligent weather pattern detection systems, advanced atmospheric models, and new cloud seeding decision algorithms can elevate this field to new heights. Hosting such an array of topics was precisely the vision behind establishing the UAE REP, which was launched in 2015 under the patronage of His Highness Sheikh Mansour bin Zayed Al Nahyan, Deputy Prime Minister of the UAE, and Minister of Presidential Affairs. It is thanks to the drive, determination, and clarity of vision put forward by the UAE's leadership that the Emirates has become a hub of rain enhancement activity, ever at the beating heart of knowledge transfers that stimulate debate and discussion, taking the sector forwards to provide a better quality of life for all. With this foundation in place, the UAE continues to advance rain enhancement research. In the first 3 cycles of the IREF, 49 scientific articles have been published, of which 41 are in Q1 international peer-reviewed scientific journals, obtaining 4 new patents along the way. Our network of more than 1,450 researchers across nearly 70 countries have engaged almost 650 scientific institutions through 370 research proposals submitted in our first 3 cycles. Moving into 2021, we are faced with a brave new world. To meet the challenges of change, I'm delighted to announce that the UAE Research Program for Rain Enhancement Science is entering a new phase. We are launching a 4th cycle. Submissions for this new cycle come with a new award mechanism to promote even higher standards of excellence in our quest to advance our research projects, to develop new synergies, and strengthen international cooperation. To everyone here today, this is your chance to write the future of our industry, to lead us towards a world characterized by water security, not scarcity. Ladies and gentlemen, on behalf of the program and the National Center of Meteorology, I extend a huge thank you to all our worthy teams for their tireless efforts despite the year we've had, and our valued stakeholders around the world for their continued and crucial support. It is our great privilege to host you, though virtually, for what will be 2 days full of listening and learning from the brightest minds in our industry today. Thank you and welcome.
Those were some valuable remarks relayed to us by Mrs. Alia Al-Mazroui. We extend our thanks to her very much. Now, we invite everyone to watch a short video because a picture is worth 1,000 words on the selection process of UAE REP's 4th cycle.
Creating hope for humanity. Advancing science and technology of rain enhancement. The UAE Research Program for Rain Enhancement Science, the innovative international research initiative, is offering grant assistance to selected teams of researchers, technologists, and scientists who are developing innovative solutions in the field of rain enhancement. UAE REP is incentivizing these brilliant innovators to tackle water scarcity and ensure that future generations will not suffer from the risk of water shortage. A technical evaluation committee, alongside ad hoc reviewers, will assess these proposals. In October 2020, the programme announced the target research areas of its 4th cycle. Now, in January 2021, the call is open for submission of letters of intent and brief pre-proposals. 16th of February 2021 is the recommended deadline for submitting the letter of intent. While the deadline for submitting pre-proposals is the 18th of March 2021. The Technical Evaluation Committee will then convene in May 2021 to shortlist the pre-proposals and invite the selected candidates to submit their full proposals by the 26th of August 2021. Then, the committee will reconvene in October 2021 to review the full proposals. To ensure rational and unbiased decision-making, judgment will be based on a standardized scoring matrix of 5 criteria. The committee will then nominate the finalists, from which the winning proposals will be chosen and announced in January 2022. In working with our future awardees in the next 3 years, we hope to accelerate innovative solutions that allow us to live in a world free of water stress, as part of our continued commitment to water security.
We hope that we can continue to come up with innovative solutions towards attaining water security through the support of the National Center of Meteorology and the UAE Research Program for Rain Enhancement Science. Ladies and gentlemen, we would like to start the forum today with a panel discussion on the outlook for global water security in light of climate change, followed by 2 sessions, transitioning from research to operations in rain enhancement, case studies and roadmap, artificial intelligence and intelligent system applications in meteorology and rain enhancement. As part of the panel discussion on outlook for global water security in light of climate change, we will hear from international experts on the topics of water security and climate change. To open the session, let's listen to His Excellency Dr. Abdullah bin Mohammed bin Hayf al-Naimi, the Minister of Climate Change and Environment, as he is delivering the keynote speech.
Distinguished guests, ladies and gentlemen, it's a pleasure to join you at today's panel discussion. I would like to extend my sincere appreciation to His Highness Sheikh Mansour bin Zayed Al Nahyan, Deputy Prime Minister and Minister of Presidential Affairs, for his continued patronage of this important event that addresses the crucial issue of global water security. I also thank all the researchers and staff of the National Center of Meteorology and the United Arab Emirates Research Program for Rain Enhancement Science for their pioneering work. In the 20th century, water usage surged at more than twice the rate of population growth. At present, about 4 billion people experience water scarcity for at least 1 month per year. By 2050, 40% of the people are projected to live under severe water stress, including almost the entire population of the Middle East. Climate change will not only make the situation worse in currently water-stressed regions, but also generate water stress even in some of those regions that have sufficient water resources today. In addition to the depletion of groundwater, land degradation, and desertification, and an increase in water consumption due to rising temperatures, climate change poses risks to water-related infrastructure. To tackle climate change, we launched the National Climate Change Plan. As part of the plan, we developed the National Climate Change Adaptation Program that aims to assess the impacts of climate change on our key sectors: energy, health, infrastructure, and the whole environment. It identifies the risk that demand urgent action and provides feasible solutions. Among the adaptation measures that are available to us today, rain enhancement has the potential to play a significant role mitigating drought and reducing temperatures. Addressing water scarcity is also a priority area in the UAE second nationally determined contribution under the Paris Agreement. To address water stress, we are following an integrated water management approach. We have adapted the United Arab Emirates Water Security Strategy 2036 that aims to ensure continued and sustainable access to water. The strategy's objective are to reduce potable water consumption by at least 20% and increase reuse of treated water to 90% by 2036. As the United Arab Emirates has limited freshwater resources, desalination is the largest source of potable water for us. We are working on decarbonizing water desalination through reverse osmosis, which electrifies the process, partially using renewable energy instead of relying on methods that burns gas. We are targeting an increase in the share of reverse osmosis-based desalinated water in the potable water supply mix to 50% by 2036. We are also implementing initiatives to reduce water losses and consumption, in addition to the introduction of green building and product standards, building retrofit initiatives, and water tariff reform. Government authorities have been running awareness campaigns to promote behavior changes among consumers. Ladies and gentlemen, I wish you a productive participation in the discussion and look forward to the outcomes of this event. Thank you very much and enjoy the day.
Our thanks are extended to His Excellency Dr. Abdullah bin Mohammed bin Hayf al-Naimi for these insightful remarks. And now, ladies and gentlemen, as well, we welcome you back again to our first panel discussion, the outlook for global water security in light of climate change, that I have the honor to moderate. Allow us first to introduce our panelists, and they are Dr. Rupa Kumar Kohli, Professor Mansour Al-Mazrou'i, and Mr. Qais Al-Suwaidi, and Dr. Saeed Al-Salmi. Welcome, everyone, and may I hear an okay from you since we're hosting this virtually? I'd like to have a very humble sound check. Can you read me?
Yes. How are you? This is Mansour.
Okay. Saeed.
Lovely. All together in union. Thank you. We really appreciate that. I'd like to just make one housekeeping input here for our distinguished audience. We will be going through this panel discussion, and an opportunity for questions to be asked will be opened during this panel discussion. Just make sure that you identify yourselves, the entity that you represent, should there be one. And lastly, and more importantly, make sure you dedicate the question to one of our panelists. With that, I'd like to start our promising panel discussion, and my first question is for Dr. Rupa Kumar Kohli. A very good day to you, and thank you for being here with us, as well as all of our panelists. Let's talk about the term, Doctor, climate change. It has been exchanged and quite often in the recent decade. And we have been dealing with climate change's effects of course, in modern times right now. However, some of which we are already witnessing in terms of these effects. Can you explain this to us, the term climate change? I mean, What does the word or the term even mean to different regions all around the world?
Thank you. My name is Rupa Kumar Kolli. I represent the International Clivar Monsoon Project Office at the Indian Institute of Tropical Meteorology, Pune, India. It's a pleasure to be part of this panel discussion, and it's an honor. And I thank you for inviting me. Coming to the first topic that was introduced, I must say that climate has never been constant, and it will never be. Our planet has witnessed many catastrophic climate excursions, causing large-scale extinction of ancient life forms that we all know. But these were all natural and mostly slow changes spread over thousands to millions of years. However, climate change has become a defining issue of our times, with increasing global realization that human actions are resulting in unprecedented and irreversible changes in the Earth's climate within the span of our lifetime. We have solid evidence that the atmosphere and oceans have warmed, accompanied by sea level rise and a strong decline of Arctic sea ice and other climate-related changes. The Earth's average surface air temperature has increased by about 1 degree centigrade since the last century, with over half of the increase occurring after the mid-1970s. The impacts of climate change on people and nature are increasingly apparent. Unprecedented flooding, heat waves, and wildfires have caused enormous damages. Habitats are undergoing rapid shifts in response to changing temperatures and precipitation patterns. Scientists have conclusive evidence that recent climate change is largely caused by human activities. From an understanding of the basic physics, comparing observations with models, and fingerprinting the detailed patterns of climate change caused by different human and natural influences. Greenhouse gases, whose increase is unequivocally attributed to climate change, naturally occur in the atmosphere. However, human activities have significantly disturbed their natural balance, though through globally rampant and rapid emissions that cannot be quickly removed by the slow natural processes. The speed of the current climate change is faster than most of the past episodes, making it more difficult for human societies to adapt. The present level of atmospheric carbon dioxide concentrations is almost certainly unprecedented over the past million years. There remains a range of estimates of the magnitude and regional expression of the future change, but increases in extremes that can adversely affect natural ecosystems and human activities and infrastructure are expected. There are three major ways in which global warming will manifest in terms of changes in the regional climate. Melting or forming of ice, changing the hydrological cycle, which has implications for water resources and river basins, and changing currents in the oceans and air flows in the atmosphere. And in particular, coastal regions and small islands will suffer severe impacts of sea level rise. So these are all part of climate change, which need to be kept in mind for us to actually deal with them. I think this can introduce the topic of climate change. Thank you.
Thank you, Dr. Rupa, for shedding light on this. And we have to shed light on this because we are merely tenant on this planet. We have inherited these lands and we are going to give it and pass it on to futuristic generations. It is only common sense that we preserve it to make sure there is functioning soil and climate that we live in. I'd like to move with my next question to Professor Mansour Al-Mazrou'i. Thank you very much for joining us. And here is a question. I've got a lot of them written down here. You have published a number of studies related to the impacts of recent climate change on a number of meteorological variables. Now, including temperature and rainfall, Professor, in the Arabian Peninsula. Could you give us a brief summary on the results?
طيب, okay. Now I have published more than 100 papers in recent years, and we get many results regarding the water and temperature and other parameters. But mostly, what I would like to say about some comment of the results, we have major finding. One of the major finding of these studies. This is based on recent IPCC reports, CMIP6. I'm leading author in IPCC reporter now. And what we found that in CMIP4, CMIP3, and CMIP5, as well now as CMIP6, which is the recent data set for the global warming and climate change. What we found over the Arabian Peninsula, that the southern part of the Arabian Peninsula is going to increase the rainfall, and northwestern part of the Arabian Peninsula will get decreasing of rainfall. And this rainfall changes is really in agreement with what we found in some publication that we did for South Asia and for the Africa. So in Africa, the Mediterranean chose drought. And I remember with the WMO, we organized a workshop in Morocco, and we found that rainfall over the Arab regions in the Mediterranean was decreasing. And this one is including northwest of Saudi Arabia, Jordan, and Palestine, as well as all the Mediterranean countries. While the southern Arabian Peninsula is linked also to the eastern part of Africa, increasing rainfall, and also with the increasing trend of rainfall over South Asia. Yeah. That is the main relation of rainfall. In fact, there is another important aspect. It is the temperature. Why the rainfall is changing? Because temperature is going to soar to higher level. Our recent study we did over rainfall over GCC, we showed that temperature could reach 52 and more. And we have some records for temperature over Kuwait, over one area in the desert. It registered 54 in 2016. And Jeddah recorded 52 in 2010. So we are expecting that increase of temperature will be continuous in the future. And this is why the rainfall will come, but there will be dryness because of temperature extremes. Yeah.
Interesting insights and remarks. Thank you very much, Professor Mansour. We'll be getting back to you. I'd like to move to the next question, of course, to another panelist who actually conducted studies on climate change in the Arabian Gulf region, Dr. Saeed Al-Salmi. Welcome, and thank you very much for joining us today. And could you tell us or elaborate on your own work and the trends in the Arabian Gulf region? I mean, what do they mean for the region's water security, Doctor?
Thank you so much. This is Saeed Al-Salmi. I work as a meteorological expert at the Gulf Cooperation Council Secretariat. And I really support what Professor Mansour has indicated about the climate and the climate change that recently happened and in the future expected. I did some work in climate analysis using the meteorological station data at the Gulf Cooperation Council countries and some of model data. Some of these data series are long as started in 1942, like in Oman, and in Bahrain since 1950, in Kuwait since 1963. And I have used daily, monthly, seasonal, and annual data series. I worked in the trends of the means and the extreme indices. And what I found that the general pattern of change over Arabia is warming, and for the precipitation is drying for the last at least 3 decades. And I can say also that the area has witnessed the longest meteorological drought since at least the last 2 decades. The other thing I found, which is supported by literature, is that the Arabian Peninsula climate has witnessed a climate jump or a climate shift since 1998. The temperature goes up by at least nearly 0.8 or degrees Celsius, with combining with decrease of the precipitation. Okay. Also, there is a witness and a variation of the trends. For example, the mean temperature, including the mean maximum temperature, have increased in higher rate over the northern stations, while the southern stations shows less increasing rate. But when we come to the minimum temperature, I noticed that over the southern stations and the coastal stations, the increase is higher rate over the southern and the coastal stations more than the other stations, which shows the influence of warming over the seas, the oceans, and the sea surface temperatures. The warm extremes are increasing while the cold extremes are decreasing. And finally, we notice also that Cat 4 and Cat 5 tropical cyclones shows increasing trend, which is very critical when we talk about the economy and the impacts for future, especially over the Southern Arabia. Thank you.
Thank you very much, Dr. Saeed Al-Sarmi, for those remarks and those readings. I'd like to move with another question to Mr. Qais Al-Suwaidi. Thank you very much for joining us here today. And let's talk about scientific advances that integrate innovation. They play a role, a vital one, in combating various environmental changes. Now, specifically that of a warming and changing climate. Mr. Qais, what are the UAE's achievements in this field? And based on your knowledge of the regional and global experiences, if you could elaborate on that.
Yeah. Assalamu alaikum. Thank you very much for having me. It's a real pleasure to be here amongst these distinguished panelists, I have to say. Now, when it comes to innovation, of course, innovation has been a key priority for the UAE's government in the last couple of years. And innovation, of course, is also part of our response to climate change, whether to reduce our emissions, our carbon footprint, or to adapt to the impact of climate change. Now, one has to, of course, say that this region has been well adapted to its harsh environment. The desert environment we have, the high temperatures, the very low precipitation, water scarcity, and so on. So we are already adapted. And part of that adaptation is the innovation that the world has been witnessing in the last couple of decades, whether when it comes to cooling or water desalination. So, but then again, with what we heard from the previous panelists as to the impact of climate change, what we project in terms of new challenges in the future, these already harsh environment in our region might aggravate further, and new technologies, new innovations, new ideas have to come in place to help us adapt further and better and build resilience to the impacts of climate change. So perhaps one key area is for example, tackling water scarcity is the rain enhancement program that the NCM runs. The impact of this program, of course, has been witnessed, and we are hopeful that more and more positive impact this program is going to have in the future, especially with the lowering water tables across the country, reduced fresh water in our aquifers, and then with that, of course, that happens due to human use. We're using more of our groundwater for agriculture and so on, but also due to decreased waterfall, or say the maintaining a similar level of waterfall. And then as well as that, you have the increase in sea levels worldwide due to climate change, and then you have an intrusion of seawater into the freshwater aquifers, especially the coastal areas. So there's a serious challenge when it comes to rainfalls, when it comes to water scarcity. Perhaps another key area also that the UAE is trying to pioneer and be an international leader in is addressing food security. So food security is, of course, a real challenge for us in the region, again, given our environment and water scarcity. And then we've seen the impact this can have and the repercussions of being dependent on food imports for your day-to-day nutritional needs during the pandemic. But we're going to witness more of this perhaps in the future due to climate change, especially when countries that are impacted by climate change. These are the countries which we depend on our when it comes to our food supply. So if one country is impacted, perhaps you can go with another. But if more than one food basket is impacted, of course, the challenge can be great. So perhaps one example is vertical farming, agri-tech. We heard in last year the announcement by Emirates Airline and One Crop of creating vertical farming in the country. And we have the investment is, of course, a multi-million-dollar investment in an area of 12,000 square kilometers, but equivalent in its production to 3.6 million square kilometers of the conventional, food production methods, but then saving at least 99% of water compared to open farming. So there are a couple of other areas also of innovation. Perhaps we can mention them later. That the UAE is trying to implement to prepare for climate change.
I see. Thank you very much, Mr. Qais Al-Suwaidi, for those remarks. I wanted to go with a question with Dr. Saeed Al-Sarmi. I think he will get back with us, unless you can hear us, Dr. Saeed. Can you hear us? A bit of a technical issue. I think he will be back. Let me move on. Professor Mansour Al-Mazrou'i, we have a question for you. If you could tell us about the work that you have participated in the atmospheric influences on the region's climate. Now, in your opinion, what role can this research play in being better prepared to face water scarcity challenges?
Yeah. Can you repeat the question again, please?
All right. Yes. Now, in your opinion, what role, when we talk about, of course, your work that you have participated in the atmospheric influences in the region's climate, in the Arabian Gulf's region's climate, what role can this research play in being better prepared to face water scarcity challenges?
Yeah. In my opinion, we first need to have a common platform to study climate change in more details. Now we have scattered, groups from Oman, from UAE, from Kuwait, from Bahrain, and Saudi Arabia, and other countries. What we need now, actually, all the regional scientists had to sit together and put for GCC a platform to build for further analysis of atmospheric parameters. For example, we need to have a high resolution of climate data. We cannot do this without full collaboration with each other. So I recommend for Dr. Saeed to have a platform for integrating all the activities of the region. Now, every country is separate, doing its own analysis and the resources. Now we are having a supercomputer, for example, and now I don't think in all the GCC countries they have supercomputer that they'll be able to run their models. Now we go on resolution of GCMs from 300 to 100. Now, even RCM can go up to 5 kilometer resolution. but you cannot do it for just only one region, one small country. You need to do it for the all over the country, all over the GCC, and many impact studies and adaptation strategy must be built on high quality high quality projected data. If you don't have the data, you cannot build a trust on the future planning or adaptation or even impact studies. So that is my request.
Thank you very much, Professor Mansour. Dr. Saeed, what do you think of what the professor just said? He's calling for a collaboration. He's calling for archiving and filing all of those researches, numbers, and readings together to form a better understanding and form a better picture of what would the climate be tomorrow and how to avoid a certain scenario. What do you think of that?
Well, I fully agree with Professor Mansour, and I thank him because Professor Mansour, he's the director of the Center of Excellence of Climate Change in King Abdulaziz University, and he has an initiative to establish or start with such, gathering and collecting all the efforts when he organized the first conference on seasonal climate over the whole Arabia. So Dr. Mansour, Professor Mansour, is well known with his thoughts and his works, and there are some similar initiative, but to a less extent is less known and less small size than what Professor Mansour is talking about. Actually, the other point that from what research already done in the region, there are a lot of work which shows consensus agreement of how the climate in the region has been changed and where are the climate parameters are going on. So the other point is why we should not start doing some actions, some real actions on the fields, on the strategies to tackle, to adapt, and mitigate the climate change in the region. As Professor Mansour said, he has already published 100 papers in the region, which is, is a treasure for the whole communities here, so that we should work on these results and start raising the awareness of these conditions and the possible future conditions. So in one hand, we should, yes, work on science and build this archive, but on the other hand, we should also start working from whatever research has been already accomplished, and the results are really shows some sort of consensus in the output.
Dr. Saida, we'll be definitely getting back to you, since each and every member here, all of you, all of our panelists, they have their own insights and their own readings. So I will be getting back to you with a question. But right now, I would like to go to Dr. Rupa. Dr. Rupa, I want you to think of the following sentence, of the following statement. A regional approach to the studies of climate change and collaborations to combat it is the advised way to go moving forward. How would you elaborate on this?
Thank you. Actually, I think both Mansour and Saeed have actually provided excellent foundation to this topic, which I think I can build on to bring more specific aspects to it, and also bringing the water sector into focus. As you know, climate variability and change have come to be widely recognized as the major drivers to influence water resources, both in planning and management. So in that context, we need a more holistic approach, spanning the entire climate water continuum to help countries to derive optimal benefits for adaptation and risk management requirements. And another thing actually Mansoor and Said also have alluded to is that climate has no political boundaries. So there is a need for all the countries to work together. So in that context, shared climate challenges become acute on regional scales, and we need to address them in a sustained collaborative framework through regional approaches to carry out and communicate regional assessments of climate in the past, how climate has changed, how it is changing now, and what are the future expectations. So in that sense, a regional approach in generating climate information is a fundamental requirement, even if there is adequate capacity in the national scale, because the countries share common regional climate drivers, and it is important to ensure consistency at national and subnational scales to take up adaptation and mitigation efforts. So in that sense, multi-country coordination of climate change impacts and also on transboundary hydrological systems needs enhanced data and information sharing. In fact, in this context, the IREF region is fortunate that there is a pioneering initiative in terms of the regional initiative for the assessment of climate change impacts on water resources and socio-economic vulnerability in the IREF region, also called RICAR, in which Mansoor and Said have actually played an active role. This is coordinated by the Economic and Social Commission for Western Asia, ESCWA. This is a pioneering initiative that provides a common platform for assessing, addressing, and identifying regional climate change challenges, and which in turn inform dialogue, priority setting, policy formulation, and responses to climate change at the IREF regional level. And RICAR has implemented what is called IREF Climate Outlook Forum, IREF COF, and also a GCC COF for the GCC countries for regional seasonal outlooks. So the same mechanism actually can be expanded to cover regional climate change assessments. So to sum up, actually we need a sound climate rationale based on objective assessment of the current status and also expected future states of the climate, particularly on regional, national, and basin scales. This is essential for decision making in climate change adaptation and mitigation actions. Thank you.
Thank you very much, Dr. Rupa. Now, I want to move to another question, but I will take a risk and ask it to Mr. Qais Al-Suwaidi. There is no risk on you answering it, Mr. Qais. It's just that we're running out of time. And we have another question that all of our dear panelists should answer it. Mr. Qais, in which water resource challenges does the Ministry of Climate Change and Environment classify as the most important ones to address at the local level? And could you please give us a brief on, a very short one, on the initiatives currently being undertaken?
Yeah, sure. Although I had an opinion I was intending to weigh in on the discussion just having, but in any case, now when it comes to that's fine. I was just going to say that the way we're doing it at the UAE, the way we realize the challenge that Dr. Mansour, Dr. Saeed, and Dr. Rupa Kumar are mentioning is that we started with the adaptation work, so with thinking of the risks that current knowledge, current studies tell us about, and then trying to find ways to adapt to these risks. And then it's just making these studies relevant to policy and decision making. I think there's this missing link, and this is what we're trying to do. And perhaps bridge, and maybe this can be food for thought, and maybe something we can discuss later with the panelists. And now when it comes to water scarcity, of course, now, the UAE and broader region, they're part of the most water-stressed regions of the world. They're really the most water-stressed region of the world. But then when it comes to water consumption, we were one of the most water-consuming countries. And of course, this has been enabled through technology and so on. But then this may not continue with our current know-how and technology in the future. It can become more costly and so on. So the UAE, back in 2016, the UAE adopted the UAE Water Security Strategy 2036, and it aims to do three things. It takes an integrated approach, and one is to reduce consumption. It's too high in the UAE. Reduce consumption by 20% by 2036. Increase the use of recycled water in, say, irrigation, industrial use, district cooling, and so on. And the third is to move towards towards electrifying water desalination. Again, water desalination is a very costly technology, but this is the only option we have in the country, in the broader region. So moving towards reverse osmosis, electrifying the process to reduce the impact, the environmental impact the current desalination process is having on our environment, the emissions produced due to the cogeneration process. We produce water as a byproduct of electricity generation. So there is an environmental impact, there's a climate change impact. So as part of the water security strategy, the target is to have 50% of our water production from reverse osmosis. As of now, we have Al Tawila in Abu Dhabi. By 2022, it's going to produce around 1 million cubic meter of desalinated water through reverse osmosis. And in Dubai, by 2030, we're going to have another 1 million cubic meters through Hassian desalinating.
Thank you very much, Mr. Qais Suwaidi. And I'm just going to inquire about how much time do we have left exactly? Should that give us... all right, so we basically have 1 minute left. At all rates, for our dear panelists, you have graced us with your presence. The very much insightful panel discussion, the outlook for global water security in light of climate change. I'd like to express my thank yous to all of our panelists, Dr. Rupa Kumar Kohli, Professor Mansour Al-Mazrou'i, Dr. Saeed Al-Sarmi, and Mr. Qais Al-Suwaidi. You have brought the light to this virtual forum and to this panel session in particular. Thank you all very much.
Thank you very much.
Thank you.
Thank
Thank
you so
you very
much
much.
for inviting us. Thank you.
Goodbye.
Thank you. Thank you. And now, distinguished guests of ladies and gentlemen, our next item on our agenda for today is a session titled Transitioning from Research to Operations in Rain Enhancement, Case Studies and Roadmap. Part A, Systematic Approach to Evaluate New Cloud Seeding Nanomaterial. Dr. Dian Terbalanche will be the moderator for this session. And we will start this session with our first speaker, Mr. Sufyan Farah, who will be presenting on the deliver mechanism of novel nano-coated seeding salts into clouds.
Good afternoon, everybody. I'm talking from the National Center of Meteorology from the UAE. I would like to give just a quick review about the activities of cloud seeding in the country here. Actually, because of deficiency of natural water resources, as well, the annual rainfall is less than 100 millimeter. The country took a commitment to enhance the natural water resources, such as rain, through the cloud seeding. They started at the beginning of 1982, and then gradually, year by year, till the end of 1990s. But unfortunately, these projects were not following a scientific basis. By 2000, the country, through the National Center of Meteorology, they contacted substituted centers such as Ankara and Witwatersrand University from South Africa. In addition, that NASA and NOAA being shared in the Unified Aerosol Experiment UAE2 in the government and the UAE. And also WMO was working as for the 2005 2005 that the price of UAE for cloud seeding. And through that tremendous activities in the field of cloud seeding till the year of 2015, that the initiative program that been announced by the National Center of Meteorology at that time, and through that 3 cycles, 2016, 17, 18, and we've got, next slide, we've got fruitful results. Now I'm going to talk about one of the goals that have been achieved by the United Arab Emirates for Rainfall Enhancement Program, is the new agent seeding material to improve the cloud seeding process by activating the condensation process in the cloud and increasing rainfall amount. Also, this new material actually activated or increased the super cold water droplets in the cold portion, and that enhanced the ice nucleation process and precipitation. Next, please. Talking about the design and synthesis of the microstructure of the new novel material, if you look to the left, it illustrates that most of these particles are mostly uniform and homogeneous in sizes, while the hygroscopic that we conventionally used in cloud seeding has different range or expand range from 0.3 to up to 15 microns. But here you can control, as you are using the jet milling, the size distribution of the particles. The coating, it is normally potassium chloride coated with the titanium dioxide with 30 to 50 nanometers. Because of that, they are saying that utilizing the nanotechnology in a new novel cloud seeding material. Usually the hygroscopic particles, like naked salt particles, that play an important role for absorption, condensation of water vapor molecules, and eventually the deliquescence of sodium chloride crystal occurred at the same time and the same time of hygroscopic interference between NaCl and the moist air. While if you look to the right-hand side, this frame is illustrated how the porous of the shell, and that actually will make the material hydrophilic in addition to hygroscopicity of the salt particles inside. This porous actually will decrease the demand saturation vapor pressure for the water growth inside. So there will be greater potential to enhance rainfall from the cloud by using these new novel materials. Next, please. Testing or validation of this novel material has been done at the laboratory in Khalifa University. That been the environmental scanning electromicroscopic for wet sample. It shows that the naked salts to the left-hand side has been delayed in deliquescence, but the right-hand side for the coated particles shows how the particle grow earlier before the sodium chloride. Other approach for validation, the new cloud seeding material has been done in the cloud chamber in Russia, and they exposed the inner atmosphere into 100 relative humidity in the container, and the concentration of that water droplet size was between 10 to 25 micrometer, which is crucial to rainfall. You know, there is a critical size for the droplet for collagen and coalescence process. While if you look at the right-hand side, the left one is the coated salt particles and the naked salts to the right edge of the screen. You can see the number of larger particles has been increased comparing to the naked salts. that will enhance the collision and coalescence process, and then eventually the increase of rainfall. Now, after that, so it has been tested in a laboratory, a two-dimensional test, and also in a three-dimensional test in the cloud chamber. And all of this has been achieved the requirements for the seeding material to be suitable for seeding process. But now the delivery of this material into the cloud, because this material is very sensitive and can easily clog, and can be easily clogged because of high relative humidity in the base of the cloud, and it can decluence within 68% of relative humidity. So they thought about the atomizer, but unfortunately, this atomizer, dry atomizer, can be blocked easily. Because of that, the Department of Research and Development worked together with the Emirates factory for weather enhancement, and they came out that we are going to use the same body flare that be filled with this material, and will be with different strategy to eject the material instantaneously into the cloud. There are many goals can be achieved by using these techniques. There are no need to renew a safety license from different authorities that is already available, or for the flare bodies, and as well as the dispersion of this material is instantaneous. This actually will save time in the seeding process, which is crucial to the some clouds, specifically that clouds with the short life period. That actually will add the potential to seeding efficiency. Apart for the two reasons in above, this actually will give encouragement to the countries that they are already using the hygroscopic flares to use these canisters filled with the the nanomaterials. Next, please. Usually, once moving to the target, the cloud, he'll start to search for the proper portion of the cloud. And once he finds that proper portion of the cloud with good updraft, he will try to seed that area. And usually it takes 3 to 4 minutes, which is difficult for the aircraft to maintain the location because of continuous movement. The benefit of, next please. The benefit of using these canisters, that will, the pulsing or ejecting of this material will be instantaneous, and will be ejected into that proper portion that usually the pilot is looking for. This technique is more effective compared to the conventional use flares, but more study is used to be simulated in the models. The simulation model for the nanotechnology, it was showing that this material has an active about 1.8 times compared to conventional flares. Next, please. In open atmosphere, actually, we did some experiments to measure the size distribution of this material, and it was achieving the optimal size. And that size was 1 to 10 with the median of 5 micron. The 5 micron is optimal actually to the cloud seeding in the country and in the warm clouds. Unfortunately, we didn't yet have a good class to test this material in the cloud, but very close. We will have this approach in West Texas, and Dr. Roloff will talk more in this session after I finish. Thank you very much.
Our thanks for Mr. Sufyan for his time. And now we would like to introduce our second speaker of the session, Professor Istvan Gersti, who will share a presentation on a comparison of the efficiency of different seeding materials by using 1D partial method.
Yeah, I am here. Thank you. So the purpose of the research was that to see the efficiency of hygroscopic seeding in the case of the different environmental condition. I mean that the different background aerosol size distribution, chemical composition, and different cloud dynamics. Please go back. Okay, thank you. So to do this with, please, next slide, please. Okay, so to this research, we developed a 1D parcel model, and we focus on the simulation of the diffusional growth and the drop formation on the different type of aerosol particles, not only in the saturated condition, but in the case of the undersaturated conditions as well. And we categorized the aerosol particles on the base of their hygroscopicity, and we simulate the diffusional growth of water drops in the different type of aerosol particles, not only in the case of the background aerosol particles, but in the case of the hygroscopic seeding materials. So this type of simulation allows us to have a parallel simulation of the diffusional growth and the competition of the drops containing different type of aerosol particles for the available vapor content. Please go to the next slide. So because that's the impact of the diffusional growth can be tiny, so we also involve the simulation of the collision coalescence, because this type of process can impact the effect of the, can amplify the effect of the diffusional growth. As you can see in this figure, so we use two different type of scheme to simulate the growth of the drops. Under the cloud base, about 100 meters below the cloud base. So we use a moving beam scheme to simulate the diffusional growth, and 100 meters above the cloud base, we change the scheme to the fixed beam scheme, the collision coalescence as well. Okay, so because there's the 100 meters above the cloud base, the solution term is negligible. So this is the reason we can move from one scheme to the other scheme. Okay, so we use different type of background aerosol size distribution and seeding aerosol particles as well. So we use the data of two research field programs. So one is the United Arab Emirates research program, and the other one is the Queensland Cloud Seeding Research Program. We made a number of different sensitivity tests, more than 80 running was made. As you can see here, we investigated the impact of the different type of seeding material, different concentration of the seeding material to involve the impact of the different dilution factor. And we also studied the impact of the cloud dynamic. I mean, we use different updraft profile. And also we see that's how the hygroscopicity and the size of the particles can impact the efficiency of the seeding. Okay, go to the next slide, please. So we try to simulate the impact of the so-called nanoparticles. And because unfortunately we don't have information about that's how the hygroscopicity of this type of particles depends on the size of the drops on these particles. So to take into consideration of this uncertainty, we use a function to describe how the hygroscopicity depends on the size of the drops formed on it. And as you can see here in the equation, you can see an X factor, and we use different X factor. I mean, in the simulation, we use X equals 0.1, and we use X equals 1.0. And you can see on the curve, so how the hygroscopicity depends on the size of the drops formed on the aerosol particles. So as you can see here, when the x is equal to 0.1, the hygroscopicity doesn't decrease so dramatically, but in the case when the x equal 1, the decrease is more dramatic. Please go to the next slide. So here you can see some preliminary results about the simulation. The first row shows the size distribution of the background aerosols. This type of aerosol were observed in the United Arab Emirates program. And the size distribution of the aerosol particles are the same, but the size distribution hygroscopicity of the seeding material are different. So in the first column, you can see how the nanoparticles impact the seeding. And the middle, you can see that's how the I-70 type of particles impact the seeding. And the last, you can see how the NCM particles impact the seeding. In the first row, you can see the related size distribution of the drops. The black line shows the background. That's what's happened in the case of the background. So it means there is no seeding at all. We call it control cases. So the back line shows the size distribution 1 kilometer above the cloud in the case of the control cases. And the red line shows the impact of the seeding. So as you can see here, in the case of the nanoparticles, the impact is significant. But in the other two cases, the impact is negligible. So even more, if you see the last column, so that's tiny overseeding occurs, it means that the size distribution of the drops formed due to the seeding a little bit narrower than in the case of the control cases. Please go to the next slide. And also we investigated what's happened when we have a different type of background aerosol particles. So here you can see two columns. In the first column, we can see what's happened when the aerosol size, initial aerosol size distribution is United Arab Emirates observation. And the second one shows what's the size distribution in the Queensland program. So the main difference is that you can see here, that's the blue ellipsoid. So one difference is that that's the missing of the coarse particles in the case of the Queensland observation. And the other difference is that that's the concentration of fine particles is significantly larger in the Queensland observation. So in the first line, you can see the impact of the seeding in both cases. And have to emphasize that the cloud, updraft at the cloud base is about 2 meters per second. So that it means relatively weak. I don't show the figure about that, but when the updraft is stronger, so we can see a much more smaller impact of the seeding. But if the updraft is weaker, it means 2 meters per second. So you can recognize the significant difference in the two cases. So why in the United Arab Emirates aerosol particle size distribution, we can see a negative effect. So that means that the seeding reduces the breadth of the size distribution. And but in the Queensland case, we can recognize some broadening of the size distribution. So in the first case, the effect is negative, and in the second case, the effect is positive. Okay, next slide, please. Okay, so that's the other important issue. If we want to see the efficiency of the seeding, which strategy is better? To inject more and a larger particle, or to inject less, so they inject less but larger particle, or inject more but with smaller size. So to do this, to make a decision about that, we have to see how does this different strategy can enhance, can promote the formation of the larger drops at the cloud base. So this figure shows that's the relative, what's happened when the relative humidity is near to 1. That means we are near to the cloud base. And what you can see here in the figure, you can see different size, aerosol sizes from 0.1 micron and 1 micron and 2.5 micron in diameter. And you can see the equilibrium sizes at the solid lines. At the equilibrium size means the solution of the right-hand side equation. So that means that's when the diffusional growth is equilibrium. You know that it means it's equal to 0. So we can solve this equation and we can have the solution. And the solution is shown by the solid lines. Of course, larger the particles, it takes longer time to reach the equilibrium size. So this is shown by the dashed line and dotted line. So what we can see here, so that's when the aerosol size is tiny, it means a 0.1 micron. So that means in this case, there is no chance to produce larger drops, and there's a few micron, even the hygroscopicity is larger. So if we increase the size of the aerosol particles to 1 micron, so in this case, we can see a larger, we can have a chance to have a larger drops. And if you increase the size to 2.5 microns, so in this case, that's theoretically very large size, we can get a very large size of particles, but due to the time constraints, in reality, this size can be significantly smaller. But even if we take into consideration the time constraint, so we can recognize that larger the drops, larger the chance that we have larger drops, larger the aerosol particle, the larger the drops that we can have at the cloud base. Okay, so this is the theoretical background, and now we can move. So that's to see what we had in the case of the simulation. Next slide, please. So here you can see what we have. So I made a simulation. You can see the results in the two columns. And the left columns, you can see when the size, the concentration of the background aerosol particles is relatively small, but their mean size is large. And in the right-hand side, you can see the difference when the size is small and the concentration is relatively high. And even to see that we can have a larger effect, we have I give a larger hygroscopicity in the case of the smaller particles as large as it possible. So that means in the case of the small particles, I suppose that the hygroscopicity, the parameter described the hygroscopicity is near to 20. And in the other case, I suppose that's the, okay, so we have less but larger particles. So in this case, that's the hygroscopicity was equal to the hygroscopicity of the salt particles. And the first row, you can see, that's what you can see the size distribution of the drops comparing with the control cases when the cloud-based updraft was about 5 meters per second. So what we can see here, so when the mean size of the seeding material is larger, so that the size distribution it was significantly broader due to the seeding. But when the concentration of this seeding material was high, but the size was small, even that hygroscopicity was large, the impact of the seeding was negligible. Next slide, please. Okay, so that means, as I mentioned you, I had a number of simulation, more than 80. So that's I tried to summarize the results to make some statistical analysis of the results. So, and I suppose, you know, that's how that's the cloud microphysics of the clouds can impact of the efficiency of the seeding. To measure the efficiency of the seeding, I use the parameter of the reflectivity 1 kilometer above the cloud base. As you can see here, that's E is the change of the reflectivity from between the seeded and the control cases. And now I see that's how the efficiency of the seeding depend on the parameter R. And what is the meaning of this parameter? This parameter involves the term how the seeding can increase the vapor uptake due to the seeding. So this is the first term in this equation. So I see that the ratio of the cloud liquid water in the control and seeded case 100 meters above the cloud base. So this is the 1 point. So that's the hypothesis is that that's the presence of the hygroscopic seeding can enhance the vapor uptake, mostly below the cloud base. And the other possible impact, that's how the seeding changed the number of the activated aerosols. So that's this inversely, the efficiencies, I suppose that's efficiency is inversely proportional with this term. So that means if we increase significantly the number concentration of the activated particles, so that means we reduce the mean size, that means it will reduce the efficiency of the seeding. And you can see here the results on the left-hand side. So you can see that we can have a positive impact when the E is larger than 0. And if you see that the E is less than 0 when the R is less than 1, so that means then we are not able to, the seeding is not able to increase the vapor uptake, or it significantly increase the number concentration of the activated aerosols. The efficiency of the seeding can be negative. It means that the size distribution of the drops 1 kilometer above the cloud base decreases due to the seeding. And we suppose that the consequence of this reduction can be less precipitation. And if we go to the what's happened when the R is larger than 1, we can see that the scatter is relatively large, but we can have a significant increase when the vapor uptake is significantly increase due to the seeding. Okay, please go to the next slide. So the summary here, so that's our hypothesis about the efficiency of the seeding seems to be work. So that it means we can increase the vapor uptake due to the seeding, and we don't increase significantly the activated aerosol particles. We have a chance to have a positive effect of the hygroscopic seeding. And the other important point, so that's how the characteristics of the background aerosol particles can impact the efficiency of the seeding. So what we found, that's the efficiency of the seeding only slightly impact of the hygroscopicity of the fine particles. Mostly the concentration is important characteristic of this type of particles. But if we see what's happened in the case of the coarse particles, the situation is more complex. It means we can see a significant impact of the coarse particles, but only when the abduct is relatively weak and the concentration of the fine particles is large, and the hygroscopicity is also relatively large of the coarse particles. So if we have a strong updraft, in this case doesn't matter, but if we have coarse particles, and it doesn't matter what type of coarse particles is there. And finally, some message about the seeding tragedy. So my simulation shows that the size is more important characteristics of the seeding material than the hygroscopicity from the point of view of the efficiency of the seeding. Thank you very much. Thank you for your attention. Please, next slide. Okay, thank you again.
Our thanks for Professor Istvan for this insightful and very rich presentation. We now would like to welcome our next panelist, Dr. Rolf Bruingents, to join our two speakers, Mr. Sofian Farah and Professor Istvan Gersti, in the panel discussion. Please welcome them.
So good afternoon, colleagues. I hope you can hear me. We are still in session 1, which deals with the transition from research to operations in rain enhancement, case studies, and the roadmap. And the specific presentations that we've just heard now from Mr. Sofian Farah and Professor Istvan Geresti related to the systematic approach to evaluate new seeding nanomaterial. So this is an exciting new development that happened thanks to the UAE IREF program, where we have something new in terms of seeding material for the first time, probably in the past 20, 30 years. It's a difficult path from developing something new in the laboratory and then systematically taking it into the real atmosphere and eventually into operational seeding. And so in the discussions you've heard so far, you heard Mr. Farah explaining the long history in cloud seeding and rainfall enhancement in the UAE. But from Professor Estefan Geresti, you also heard the important role that modeling plays in this. So it's a combination of all the tools that we have as atmospheric scientists that needs to be on this issue. But not only that, there's engineering, there's IT, there's aircraft instrumentation, there's a whole range of skills. So Dr. Roelof Breinkies, he's a scientist at the National Center for Atmospheric Research in Boulder, Colorado, and he's also the co-principal investigator of the second cycle awardee with Dr. Paul Lawson in the USA. And they have started some unique work in this process to take things from research to operations. And I would just like to ask Dr. Roelof Breinkies to give a brief overview of what they've done up to now and what are the plans going forward. So Roelof, over to you.
Based on the presentations, those are both important and valuable information. During our aircraft campaign in the UAE in 2019, basically what we did is also worked with NCM to test the particle size distribution of the new nanomaterial. During the project there was a lot of work done on developing a method. We tested several methods for the dissemination of these particles, and we ended up with the flares. However, during our limited field program, we were not able to do any in-cloud measurements because the proof on the pudding is basically what happens in the cloud. Our models are limited because they have certain assumptions in terms of particle size distributions, in terms of hygroscopicity. And so these measurements are important to initially start the modeling, but the real test happens in the clouds. We were planning to do these tests in West Texas this past summer. However, during the La Nina, we had one of the driest years in West Texas and no clouds. We are standing by at the moment. We have tested the flares in Texas. They are working well. We have sufficient amount to do the test, and we are planning to do these tests in February, March, or April timeframe when we have convective clouds after the winter again. This is exciting, but especially the in-cloud measurements are really important, and to take this further in terms of our measurements in the UAE. In the context of the UAE measurements that we took there seems to be a lack of coalescence. Although there is a broad size distributions of particles, it seems like the dust particles in the tail are not always that hygroscopic, and you only get a very few large drops. So in this sense, the new nanomaterials may make a tremendous difference in that. And this is very difficult to sometimes also in the modeling, but what we did find is that coalescence is not very active in the UAE clouds. And so we are testing this in West Texas initially, which is similar to some extent to the Queensland clouds. And then basically, hopefully, further tests in the UAE may provide further results in this regard. But I think it is time to go to the in-cloud measurements and also assessing what is happening in the cloud. The UAE also has a very advanced radar network, dual polarization radars. The combination of aircraft measurements and radar measurements would really help in developing our understanding of the effects of this nanomaterial. Thank you.
Thank you very much, Roelof. So I want to turn to Mr. Sofian Farah. He's a meteorologist and cloud seeding expert at the National Center for Meteorology in the UAE. He's got a long history as as a meteorologist in forecasting, but also in the history of the whole program. And so I would like to ask him how excited he feels with his colleagues about this new seeding material, the nanomaterial that was developed by Professor Zhu and her colleagues. And what in your mind have been the most challenging stumbling blocks to move from research to operations?
Thank you very much, Dr. Dion. Actually, my colleagues are happy with these materials at this moment, but unfortunately, it's not been tested yet in the convective clouds, as Dr. Roloff mentioned. The challenging for the dispersion or dissipating this material into the cloud is mostly being done by the factor of rainfall enhancement in the country that belongs to the National Center of Meteorology. I think the most important now is going forward to test this material in the cloud. The other thing that filling this material is taking a little bit of effort, because it mostly is manual, and we are looking or searching to be semi-automatic or automatic, that for a mass production for in the future. We hope that this material will achieve the improvement and satisfy the Committee of Cloud Seeding. And we are looking to make it a revolution and make a revolution in cloud seeding. As I told you that we are overcome the dispersion, this material into the cloud to avoid the blocking or any that's from my side, yeah. And what was the other question, please?
No, it was about the challenges and the excitement regarding this new material. Now, I can just mention that Dr. Linda Zhu has brought a completely new field of expertise into the field of rainfall enhancement by bringing her skills and those of colleagues that are experts in nanotechnology to improve the efficiency of seeding material. But of course, she has now created something that's got a huge affinity for water, being very hygroscopic. So then it also creates some practical issues for the storage, for the dispersion into the atmosphere. But I think you have overcome many of those. And so this is just an example that if you develop something new, you need to think about all the practical issues of going into the atmosphere and delivering these things inside clouds. Before it's only then that you can start finding out how efficient they actually change real clouds. The modeling, of course, helps us a lot. And one-dimensional models are simple in certain aspects, but also complicated in other aspects. So they don't represent the dynamics of the atmosphere and entrainment and all those sort of things very realistically, but you can deal with the microphysics in a much more detailed manner. So I would like to ask Professor Estefan Geresdi about the interplay between models of this sort, like the 1D parcel model, and maybe working hand in hand with cloud chamber studies, and so that your observational studies in detail and the model studies can be collaborated and support each other. So I would like to hear your comments on that. And then I've got another question to you regarding the size ranges. But if you could do this one first, I would be most happy.
Okay, so that's at first, that's the interplay between the different model scale. That's the, you are right. So that's the 1D has a lot of disadvantage. Of course, that's when we try to describe the for example, the cloud dynamic. We also neglect the fallout effect and so on. But you know that if we can focus on the microphysics, so we can see that some very, very detailed description about the how, for example, that the water drops start to form even below the cloud base under saturated conditions. So that's, I think that's the first step is important, can happen in the atmosphere in the case of the hygroscopic seeding. That's what's happened under the cloud base. And after that, you know, that's a competition between the different type of particles. So I think that's my results confirmed it, that the competition is very important, you know. And so that's the reason we choose the 1D. So from the 1D model, we can move to a different direction. So one of you mentioned, okay, so that's the comparison with the cloud chambers. So that's to simulate what's happening in the cloud chamber. So that's in this case, that's the situation is that the scale is so one point of view is smaller because the size of the chamber is smaller. And in this case, we can focus on the microphysics, but to simulate what's happened to microphysics, so that we need a very good spatial resolution. So what's happened in the chamber to take into consideration everything. So in this case, we have to move into the direction of the smaller case. I mean, that's if we want to see that the spatial resolution of this type of model can be as small as a few centimeters. So this is the one way of the improved simulation and have some comparison with the observations. I think it is important, and as I know that it's getting more and more involved, more and more scientists involved. There are a number of new laboratories, and so we have a great challenge about the simulation, what's happened in this laboratory, in this chamber. So that's it. This, if you understand what's happened there, so it can improve our knowledge significantly, I think. And I think that it is another way, Roloff mentioned the field observation, to have a better understand and the comparison of the field observation, we need a large scale model. So we have to, I think that we have to move into other direction as well to see how a 3D model with larger scale, because in this case we can have a comparison with the field observation as well. So I think both direction is important. And I think that's because, you know, I just, my history, well, story, but it is not so important, but I have to mention, you know, that I started my career almost 40 years ago. So that's, I remember that's the capacity of the computer comparing with the nowadays. So that's not only our knowledge increased significantly in the last half century, but our chance to have a more detailed simulation about that. Of course, I think that the same situation happens in the case of the observation as well. So I think that the other way is also important to develop a 3D model and with good spatial resolution to understand. So that's to make a comparison between the field observation and the model results. So that's I think that these scales of the model can cover our scale in the field scale of the different type of observation. And so that's, I believe, I have a dream, you know, that the models and the analysis of the model data can help to understand the physics happens in the clouds, especially in the case of the hygroscopic seeding. So that's my dream, so as I can tell you.
Thank you very much. That makes a lot of sense. I think those two directions, not stopping to focus on the microphysics in quite some detail, in combination with cloud chambers where possible. But on the other hand, we need to move into something on a scale that is more realistic in terms of storms and clouds and rainfall, because that is the ultimate goal. We want to see what we can achieve there. But I think as we go through this discussion, it's just clear how you need to use all the tools available to systematically move from the research environment into operations. And if you miss a step, it's very dangerous because it will come back and bite you and you will have to go back to the beginning and repeat the process. Something that I also think is quite important is that you know, you must always make sure that the theory and the models and the observations go hand in hand and mutually support one another. So this is stepwise way of going about that. So before we go away from you, Prof. Istvan, can you just say that nanomaterial or not coated, if you have released normal sodium chloride particles of the same size, what would have been the difference in your modeling results?
Yeah, okay, I did it. So that's, as I mentioned, you know, that's in the case of the nanoparticles, so that's the results for sensitivity, as I mentioned, of the X factor. I mean, you know, that's how the hygroscopicity decreases as the size of the drops form on it. So that's the results for sensitive. And also when that's when I suppose that the X is relatively small, so that it means that the hygroscopicity slowly decrease with the size. So in this case, that's the effect was significantly larger than the soap particles. But when the decrease with the decrease of the hygroscopicity was relatively significant when the size decreases. So in this case, the difference was not so large. Because, you know, that's when the hygroscopicity decreased very fast. So this means when the drops reached the cloud base, so it was almost the same as the salt particles.
Yep. So yeah, that's important that we just focus on that and remind ourselves. We have another 4 minutes or so before we need to move into the next session. So I want to return to Sofian and just ask him how the seeding program is going the past year and what highlights have been achieved. And is there anything in the operational work that you do on a day-to-day basis that you've learned new things that could help in future with this new seeding material, seeding nanomaterial? Is there anything new in the past year in terms of operations that you think would be useful when you move over to start doing some serious testing on this material?
Yeah,
could be in the use of radar or anything.
Yeah, actually, nowadays we are using these nanomaterials in spite that we didn't yet receive or reveal the results from the open atmosphere using this in convective clouds in reality. But we rely on this actually at these times. And the the cloud seeding operation it is very clear to everybody now. It's been more active comparing to the previous years. That actually because of we are owning young different airplanes and pilots, and we have a division here specialized for the cloud seeding as a unit in cloud seeding operations. Hopefully that these results, also the tested results from the nanomaterial, will try to market these materials in the future, and will ask many countries that or committee of cloud seeding to use these materials in the future. But it is really obvious for the cloud seeding operations in the country has been improved, and many people now, locals, they have a good experience in managing the cloud seeding operations.
That's really fantastic. You've done such a marvelous job in the UAE.
And newly they made different studies on the target and the areas to see the difference in the outcomes of cloud seeding results.
Yeah, I think you have all the tools in the UAE now in terms of your very sophisticated radar network. You've got skilled staff, you've got excellent aircraft. And it's also very good to start practicing to use a new material, even in parallel when all the other experiments and research is still going on. So yes, absolutely not.
That's what we are doing now, yeah.
So because eventually all these things need to come together at once when it's mature enough, and we look forward and will continue to follow the development very closely. So I want to close this panel discussion now, and I want to thank the two participants and presenters, Mr. Sofian Farah and Professor Istvan Geresti, for the presentations. Very insightful, exciting work. This is one of the initiatives out of the UAE program that really ventured into new fields. And of course, Dr. Roelof Breintjes, that also joined the panel due to his expertise in this field and his involvement in the move towards applying this material in real clouds. So thank you very much, and move on to the next session.
Thank you.
Thank you all for your participation in this session. Now, let us move on to the second part of the panel, which will discuss the future of rain enhancement, roadmap, department, and challenges. Please welcome our panelists, Dr. Dion Turbalanch, Dr. Estelle D. Conning, and Professor Stephen Sims, and Mr. Omar El Yazidi. Moderating this session will be Dr. Robert Robinson.
Hello, everyone. We're going to start this part of the road mapping session. And just a few remarks about road mapping. Because of the complexity of rain enhancement sciences and all the global efforts that are being expended by different governments in academia, in industry.
Start this part of the road mapping.
It's important to develop both a vision for where we'd like to be in the future and a roadmap
because of the complexity
on how we're going to achieve that vision.
Sciences and all
so
the
a roadmap
efforts
looks at what's been done, what are the gaps,
by different governments in academia,
what's the path forward,
in industry,
and what are the milestones along the way.
So it's important to develop
so much has been done toward developing this roadmap already, and our distinguished panel today will provide insights about some of the progress that's been made.
So a roadmap looks at,
so we'll start with questions for Dr. Koning. In your role as acting head of the World Weather Research Program, can you tell us about global scale?
Good afternoon. Thank you very much for the honor to be part of this 5th International Rain Enhancement Forum. I'm really honored to be in this panel, and I thank you for inviting me. If we think about the global scale initiatives, I can start with the WMO mission statement. In this mission statement, we say that the WMO works to facilitate worldwide cooperation, and we want to foster the exchange of meteorological information, and we want to advance the standardization of these meteorological data. But most importantly, we want to build cooperation between meteorological, hydrological services, as well as academia and partners from the private sectors, to encourage research and training in meteorology. And we want to expand the use of meteorology to benefit other sectors, such as aviation or shipping or agriculture, and most importantly, water management. In the WMO strategic plan that is currently available until 2023, we have 5 long-term and strategic objectives. We want to make data more accessible. We want to have better services to our members, and in the same process, close the capacity gap, of course. But the most important for our conversation today is goal 3. We want to advance targeted research, leveraging the leadership in science to improve the understanding of the Earth system for enhanced services. This is really, really important, and this is where the research work that happens in the World Weather Research Program fits in. The WWRP implementation plan, also valid until 2023, has 4 scientific or societal challenges. And one of these is the water cycle. And that includes all the work on precipitation and cloud microphysics that also is the topic of today's discussion. The WWRP has an expert team consisting of various experts from all over the world to collaborate to improve the knowledge of weather modification work. And this expertise is then applied to promote scientific practices in weather modification research. And Stephen Sims, also on the panel, is the co-chair of this group. Thank you.
Thank you. Yes, certainly the ability to leverage all of the different activities, particularly in the research, is very important. So maybe I'll ask a question to Professor Sims. Can you share with us your insights on the way forward for rain enhancement, particularly on the role international collaborations can play? Can you give examples on research collaborations you've been involved with?
Yes, I too would like to thank you for the invitation to speak today. It's really great to participate in this event once again. It's always quite enjoyable. Look, I think the way forward for cloud seeding, for rainfall enhancement, is in many ways as it has been. It's quality research. Quality research underpins all of our advances that we make here. And in the previous session, I remember hearing Dion mention that we can't have shortcuts, we can't miss steps along the way. And I think, you know, over the last 20 years, we have seen some tremendous progress in the field. Progress in field experiments with detailed observations, new instrumentation that we haven't been able to use before. We've been able to utilize this to gain new insight, lab experiments, cloud chambers that are advancing, and numerical simulations. I mean, we are all aware of how much numerical simulations have advanced. And in the future, these are going to continue. I mean, we are seeing rapid changes, and I think this is going to really, you know, help bring a lot more credibility to the field, a lot more success to the field, a lot more visibility to the field, as we've seen. The international collaboration, well, it's essential. I mean, not only for the credibility, but also for the synergy, for the energy. I mean, we can bring in experts in cloud drone or in drones. We can bring in experts in artificial intelligence. I mean, the UAE program has been tremendously successful on this. Experts in cloud microphysics, experts in field observations. These are going to help us. These are going to help drive our way forward. Bringing in these outside, or these I don't know what's the right word here. These experts from diverse fields to help us advance the field, advance cloud seeding. As for myself, well, I probably, with regards to cloud seeding, I was involved in a Queensland cloud seeding project about 10, 12 years ago for hygroscopic seeding when there was a drought in southeast Queensland and the Brisbane area. There were scientists from the United States, scientists from South Africa. It was a very, very good international collaboration. More recently, I'm involved in a marine cloud brightening project, or I'm involved in some of the oversight of a marine cloud brightening project over the Great Barrier Reef. Outside of cloud seeding, I also study clouds and precipitation over the Southern Ocean, and there's been quite a bit of activity over that in the past few years. So thank you.
Thank you. Thank you. Yeah, I totally agree that the UAE REP has been both a benefit in terms of catalyzing all the work that's being done, but also bringing together the experts from all over the world. Sort of continuing on the theme of international collaboration, Mr. Al-Yazidi, can you tell us about current and possible future international collaborations that NCM has with other countries or international entities, you know, along the lines of advancing rain enhancement?
Yes, thank you, Dr. Robert. And I would like to take this opportunity to thank you all for participating in this such important event. And talking about the collaboration and international collaboration, which is an essential part of this initiative. To tell you about the current collaborations, for example, the National Center of Meteorology is a member of the World Meteorological Organization and its Executive Council, the Intergovernmental Coordination Group for Indian Ocean, to tsunami warnings and mitigation system. Also, the Tropical Cyclone Committee for the Indian Ocean. The executive, he's also a member of the executive office of the Council of Arab Ministers for Meteorology and Climate Affairs. In addition to that, it's also the Permanent Arab Meteorological Organization, and the also currently heading the Regional Association 2, RA2, Asia, on the World Meteorological Organization. So the NCM actually, and through this program, the UAE Research Program for Rain Enhancement Science, through National Center of Meteorology, has established collaborations with many entities from all over the world. So, for example, from China, we worked with Japan, with Russia, with Germany, also collaborations with Finland, and also both the United Kingdom and the United States of America. So we work on different aspects that deepening the knowledge of the field in rain enhancement and weather modification in general. This is again part of the driving international efforts to advance the meteorological science and advancing rainfall enhancements through these collaboration. So NCM is actually working through this initiative to fulfill the United Arab Emirates innovation strategy quest to build the leading global knowledge economy in accordance with Abu Dhabi 2030 vision. Yeah, thank you.
Thank you. Thank you. It's very true that the NCM leadership in this program has been outstanding, and we've seen so much progress made in the past few years because of that leadership. Dr. Terblanche, Dion, so switching to a little bit about the science gaps, as an expert in weather modification, so what key gaps do you think need to be addressed in science and technology to overcome both the current and future challenges in rain enhancement?
Well, thank you very much, Bob. I think it's all about cause and effect and having a clear idea of those two issues. Cause and effect. If you apply a certain seeding material to a cloud, you must be able in a stepwise way to follow the full process until rain reaches the ground or it doesn't reach the ground. So it's actually a forecasting problem. Rainfall enhancement is basically a forecasting problem. If we had ideal models, we would have been able to run simulations of seeded and non-seeded clouds and get an answer that is quite believable and true. But we are not there yet. So this indicates that we need to do quite considerable more work on model development. And model development implies also to get the microphysics right. This is an issue of scale, and it's a very complex issue. And so when you run global models, it's very difficult also to simulate at the same time things that happen at the micrometer scale. And so with improved artificial intelligence, computing systems, big data, we will eventually get there, because I believe that models will eventually be the solution to finding out how efficient cloud seeding material would be when applied in nature, so that we don't have to go through all these rather elaborate randomized seeding experiments where there's little appetite to conduct experiments that takes many, many years before you have an idea of what's really going on. So in my mind, the modeling issue is really important, and all the tools that we now have in terms of artificial intelligence and data mining and new instrumentation to try and get closer to reality. But in that process, we need skilled people. And the UAE program has been producing a new generation of people and interest in this field, which has been sorely lacking in the last couple of decades. So skilled people with a keen interest and an inquiring mind is really important to this field. People that are with a tenacity that won't give up. And then I think the issue of using the best instrumentation available these days in terms of radar, advanced aircraft instrumentation, but also other remote sensing techniques is really important. And then eventually is this thing of having open data policies, sharing information, thinking very carefully before you patent something that should actually be in the public good domain so that all the scientists can work further and refine it and make it something that is worthwhile for humanity. So international cooperation and how people manage and share data in a discoverable manner, I think is really important in this field. So I'll stop there, Bob.
Yeah, thanks, Dion. I think you've touched on many of the elements that are making this program successful. And, you know, we have this very diverse array of 9 awardees so far, but we've found that all of them hinge on understanding the basic science, the microphysics that underpins everything. So thanks for those comments. So we mentioned part of the roadmap is understanding where we are now and where we have to go. Part of where we are now has been captured in a recent WMO report. So why don't we talk about that for a little bit? Dr. de Koning, the WMO Congress approved a statement on practices for rain enhancement in 2018. Could you elaborate more on this and the role it plays in addressing the field's challenges?
Yes, certainly. In 2018, this guidance document was approved by Congress, or Council, as you mentioned, and there were 3 main statements. The first statement said weather modification should progress the strategic research to investigate and test the scientific hypotheses on which weather modification is based. And this includes a wide range of applications such as water management and climate change adaptation, as we heard in some of the previous speakers earlier today. It should also demonstrate scientific and economic feasibility, of course, and validation should be a prerequisite before something is made operational. The second statement says that we should take into account all the considerable uncertainties in this field and the challenges related to the validation of such activities. And the third, which touches on the statement Dion just made, is that there should be a data management plan that ensures that the data are available for future analyses, that the members should share their experiences and expertise in weather modification to avoid duplication and to enhance international collaboration. So these are excellent guiding principles that we have referred to many people who have inquired about this field. And thus we play a vital role in addressing the field's challenges in a systematic
way. Thank you. So Professor Sims, what research and development programs do you envision being needed to fill these key gaps in science and technology related to rain enhancement?
Well, I think referring back to some of Dion's comments that, you know, using artificial intelligence, using machine learning to try to get a better handle on this microphysics is going to be essential moving forward. This will help improve the models. But machine learning, artificial intelligence are data-hungry processes. It requires very good observations and very large quantities of observations. We know that. And so I think what we really will be seeing happening is some very, very rigorous observational programs, trying to get us these interactions, trying to show us, you know, record what happens when we inject these aerosols into these clouds. And then we can use some of these advanced techniques to improve our models. I mean, I completely agree with Dion that our models, our understanding of microphysics at present are not sufficient to help us evaluate rainfall enhancement programs. We know just on a unseeded cloud, if we use the same model, same thermodynamic setup, same environment, but we change the microphysics schemes, we can get different clouds, different precipitation amounts. So we need some considerable advancement in refining the microphysics before we can go forward too far. Thank you.
Very good. Very good. Dr. de Koning, going back to the WMO report of 2018, can you tell us about what you think is the importance of this report and maybe some of the background of why it was commissioned?
In 2017, there was a survey done amongst WMO members involved in weather modification to see what they're busy with and what the needs are. And this showed that precipitation enhancement activities are carried out primarily in response to water shortages, affecting agriculture and, of course, social needs. Cloud seeding is done in numerous countries around the world. We've learned about that earlier this morning as well, or earlier today. And it is really important to undertake such activities in a rigorous analysis methodology, that we don't just do it in a haphazard way. So the expert team on weather modification is tasked to regularly update our WMO statement and our guidelines for such practices. But in order to do something a little bit more global, the UAE kindly supported an initiative that this expert team should put together a peer-reviewed assessment of all the rainfall enhancement activities around the world. And this group worked together very well under the leadership of Professor Andrea Flossman, and an extensive report was compiled with financial support from the UAE. And this report was also published in the Bulletin of American Met Society in a shortened fashion. And the WMO is extremely grateful to the support that the UAE is giving to this initiative in the past, but also for all the projects that are currently underway and also the next phase that has been launched today to support ongoing funded projects on this topic.
Thank you. Thank you. And so Dion, as former director of research at the WMO, can you tell us something about the main outcomes and recommendations of the report? It was a big report and it had a lot of content, but maybe you can give us some of the key takeaways from that.
There were basically 5 issues or 5 headings with recommendations. The first one dealt with fundamentals, understanding the fundamentals. In terms of that, the expert team said that we need more information on the formation and growth of ice in clouds, and specifically also on secondary ice formation. They also indicated that the interaction between cloud microphysics and dynamics needs further study, the diurnal cycle of convection, the merging of storm cells. We need to understand those things better. The same with ambient background aerosols, and the analysis of historic data, where we get back to this data sharing and data archiving and data discovery issue. The second main topic was about instrumentation. The accurate measurement of precipitation on the ground over catchment scales is still a problem and needs further attention. Measurement of snowfall, hardened software systems for accurate and consistent measurement of cloud and meteorological variables. We still need a lot of work to do there. Then in terms of seeding itself, the new types of seeding agents, we heard earlier this afternoon of the process when you develop something new. It's not an easy path to follow, and it's a stepwise process and quite hard work and a lot of sweat. To determine exactly what the optimum altitude of seeding is something that's still not very clear. The scaling up seeding of mixed-phased convective clouds. Then the next one was about the issue of modeling. the treatment of condensation nuclei and ice-forming particles in models, the spatial temporal development of clouds, the treatment of seeding material in clouds, finer resolution, model intercomparisons, microphysics and the boundary layer, the dispersion of droplet distributions near the cloud base. And then finally, there was highlighted that issues related to the environment is also important. So we need to look more carefully at extra area effects of seeding. Always keep in mind the possible toxicity of seeding agents, address the issue of redistribution of surface precipitation, and then look at the whole list of possible environmental risks that could follow from such interventions. So in short, this is what the report highlighted.
Very good. That's great guidance as we develop the roadmap. Very, very thorough analysis of what progress we have now. We have about 5 minutes and we have a couple more questions. I think we can squeeze them in here. Professor Sims, you're the current co-chair of the WMO's expert team on weather modification, and you were also a reviewer of this report. So what are your insights about its outcomes? How often do you think such a report needs to be developed for the rain, for doing the roadmap for rain enhancement?
Well, I guess one of the insights, that I see from this report is just many aspects of the science ahead of us are not unique to cloud seeding. I mean, we've seen tremendous research on clouds and aerosols from climate perspective. Cloud aerosol interaction is one of the major topics when we go around to different meteorological conferences around the world. So looking at mixed phase clouds, looking at the interaction between the microphysics and the dynamics, looking at the development of convective clouds, these are challenges that are beyond just cloud seeding. So in that sense, I think there's a lot of wealth and a lot of potential to make advances in these fields. We have resources all around the world being invested in these challenges. Specifically getting into precipitation, precipitation on the ground, again, from the hydrology point of view, these are major challenges also to drive the hydrology models. So what's unique to us, though, is this beginning to end perspective of putting in the agent to seeing the precipitation on the ground. How often should we do this? Well, if you had asked me a few years ago, I would have just said 20 years because that's a nice round number. I like it, 20 years. But I mean, advances are coming much, much more quickly now. I don't know, maybe in another 10 years, we'll be ready for another one. But that was a lot of work in that last report. I think it needs to stand for a while. Thank you.
These could be decadal surveys.
Yep.
And rain enhancement is supremely multidisciplinary. So that's another aspect that makes this a grand challenge. Omar, maybe you can tell us about the role NCM has played in commissioning of this report from the WMO, with the WMO to begin with, and then where we're going with it.
Sure, thank you. So NCM has had a long-lasting relationship and partnership with the World Meteorological Organization. And the center plays an active role in representing the United Arab Emirates within the WMO's major forums for global cooperation on the science and understanding of meteorology. In 2017, NCM granted financial support and also sent a representative to attend the meetings of the World Meteorological Organization expert team on weather modification in Geneva. And the report, or the WMO report on rain enhancement, focused on the two cloud types most seeded in the past. So in winter, orographic cloud systems and convective cloud systems. and discussed different seeding techniques and requirements for the design, for implementation, and evaluation of catchment scale precipitation enhancement campaigns. Also, the peer review report that was produced was used to guide the collections of scientists and experts who met in January 2020 to determine the targeted research areas for the fourth cycle of the United Arab Emirates Rain Enhancement Program for Rain Enhancement Science. So thank you.
Thank you, Omar. I think we're at the end of our time. I just wanted to thank all the panelists. I think you've shed a tremendous amount of light on what's been done in rain enhancement and how we're going to do the roadmap, the elements that are going to make up the roadmap, and the material like the WMO report that we have to work with. So thank you very much. Have a good day.
Thank you. Thank you.
Thank you.
Thank you.
Thank you very much. Thank you for your time. And now we are glad to welcome you to our next session, which is titled under the title of Artificial Intelligence and Intelligence System Applications in Meteorology and Rain Enhancement, of course. In this session, we will examine key topics including the use of high-performance computing, artificial intelligence analytics, and many more. We will now introduce the speakers of our second session, and they are Mr. Talal Al-Qaisi, Dr. Joha Tontella, and Professor Eric Frew, and Dr. Duncan Axisa, who will give their presentations respectively. Please welcome them.
Excellent. Good afternoon, everyone. I really appreciate the opportunity from the organizers to be invited to this esteemed conference to speak to you a little bit about the Group 42 efforts with our high-performance compute capabilities and how that could lead to support with the UAE's rain enhancement program. So my name is Talal Al-Qaisi. I'm the Vice President of Strategic Projects as well as the space program here at Group 42. And Group 42 is an Abu Dhabi-based AI and cloud computing company that was established back in 2018. And we have global aspirations and ambitions in this domain. Our vision is and our aim and our objective is to help move the needle on expanding AI from its current narrow scope to a future where it'll be able to handle some generalized tasks, much like humans do. So that's the term that people are familiar with in this industry called artificial general intelligence. And we feel that this is an inevitable eventuality, that there is going to be a point in time where that is going to occur, and we want to be as prepared as possible and potentially in the forefront and lead the group of countries and companies that are working towards this eventuality. So at G42, there are several different facets that we have, but the three overarching pillars are AI research, where we have our Inception Institute of Artificial Intelligence. It's one of the most highly published institutes of AI in the entire region, and has become really a center of gravity for us in terms of fundamental AI research in the country, and is helping us with developing different types of interesting applications and solutions that many of our verticals, which I'll talk about, are benefiting from today. The other aspect is the cloud compute infrastructure that we have, and I'll talk a little bit more about that in the next few slides. And the last one is obviously our industry solutions, which is the basis of our several different verticals and business units that we have and operate within. And so this is the ability for us to support the digital transformation effort of many of the industries that we try to serve by injecting AI and technology. So we have roughly about 1,000 people today. So we've grown quite significantly since our establishment in 2018. and a great partnership ecosystem as well that has become kind of a force multiplier to us, especially with our global efforts and aspirations. And the fact that the UAE's progressive regulatory framework is something that we can take advantage of. It's the attention to the future-oriented technologies that our government here in the UAE has positions us as a private company in a significant advantage to be able to do some incredible things. We're able to access a broad spectrum of data, which is quite significant when we're trying to ingest a multitude of different data sources to our cloud, and then it provides us the ability to generate very exciting analytics and develop algorithms which translate into many innovative applications and use cases for a variety of different industries. And I'll talk about some of those here in the next slide. So here you can see the variety of different sectors that I mentioned we operate in. So there's everything from healthcare to smart cities, fintech, geospatial solutions as well, which we'll dive into a little bit deeply here today, industrial AI, energy, and so many other sectors that we're able to apply to. But these verticals are what make up the group of families that the company has. And we have several different horizontals that cut across and support and enable these different verticals. And those horizontals include obviously our cloud orchestration layer, our fundamental research organization, the data center capabilities, and our connectivity platforms as well. So we're very proud of what has been achieved so far with Group 42, and there's still a lot to come. And these achievements have happened in a relatively short time span. Most recently, a big validation to us was when Mubadala decided to take a minority stake in our company. And through that investment, we acquired Injazat and Khazna to also add to our capabilities in the IT services as well as data center domain. So it's something we're very, very proud of. And obviously we're also looking at expanding in these areas. We have some key partnerships right now that are already active, including joint venture partnerships with Abu Dhabi Holdings, ADQ, and are supporting them with the digital transformation efforts of many of the subsidiary companies. They've got about 100 plus companies or so, as well as a JV with our national oil company, ADNOC, where we're also supporting with digital transformation there, but more importantly, looking at innovative technologies and use cases and applications that we're able to deploy, utilizing AI to boost efficiencies and cost effectiveness of oil exploration upstream, midstream, and downstream. So very exciting stuff that we're doing with ADNOC in that domain. Our healthcare division is something that we're really proud of. We started off in the genomic space. Yesterday, we inaugurated a new center of excellence on omics. And we had the population genome program last year that kicked off around September, I think, of 2019. And what was interesting there is that it evolved into the pandemic management situation that we were entrusted by the leadership to deploy immediately once we knew that this was a very serious issue with COVID. And so G42 were on the forefront of companies that the UAE government turned to support with everything from rapid testing to contact tracing to even the vaccine clinical trials, which we conducted at G42 Healthcare, just based on the experience that we had in the high-end AI and genomics space. So we are hoping to get back more into the genomics space this year, now that the pandemic is a little bit more under control with the vaccine rollout. And I think preventative care is the next, big thing in this domain. So we're very, very excited about what lies ahead in this particular area as well. And as I mentioned earlier, in terms of our cloud infrastructure, we have a significant operation of like the third largest cloud globally. When you look at between the East and the West, what we afford our customers over here is having that capacity and the ability to tap into a local player that allows for scaling and different types of solutions on the AI end that could be built on top of our cloud offering. So I'm going to skip the slide and go straight into the opportunities here specific to this conference's topic, which is the rain enhancement program for the UAE. So to us, it's very important to look at ways we are able to support the effort of many of the national companies or government organizations. And when we looked at what the NCM was doing with the rain enhancement program, we realized that, and this is not something new. I think they were already looking at ways AI can be leveraged for many applications in this domain. But what we bring to the table, which I think is quite unique, is the ability to leverage a supercomputer, the 31st in rankings out of the top 500 supercomputers, our Artemis supercomputer. And the reason that a supercomputer might be needed in this type of application is, with the synoptic models, there are coarse models covering many wide areas, and the mesoscale models are much finer models. The grid, the finer the grid, the better the modeling performance, and this can only be done in a high performance computing environment. So that's where I think our capabilities can be utilized for support of the program. Also, there's another area where material research that needs to go through a large number of simulations for exploring efficiency with thousands of parallel cores. The Group 42 Cloud provides that ideal environment for such experimentation, so that you could come up with interesting new innovative materials that could be utilized to enhance the RAIN program. And then in terms of our geospatial analytics platform, here's another area that we've been applying some of our capabilities to many different sectors, but we're building this advanced geospatial analytics platform with AI inherent in it to extensively utilize the artificial intelligence approaches with respect to Earth observation data that could support critical decision-making in many different domains. The platform can easily support the UAE rain enhancement program for accurate cloud type and extent classification, and also post-event assessment of soil moisture using synthetic aperture radar satellites, especially now that we have many commercial providers of satellite data, imagery, and radar in low Earth orbit, which are going to provide for a much quicker revisit time and high spatial and temporal resolution. So, as far as the solutions that we have developed so far, I think building a time series analysis in a number of fields has given us the ability to see how this could be applied across domains. So when you think of, with the oil and gas sector, for instance, we work through our ADNOC JV and trying to build that time series, utilizing archival data as well as utilizing data that's near real time with these new constellations. And so the learnings that we have in that are easily conveyable to a sector like this, where you would need that type of time series analysis. And the general techniques can be adapted very easily. So the analysis of multiple variables that support the detection of large clouds proceedings, for instance, could be something that's of great utility here, as well as the analysis of data from ground-based sensors and evaluation of efficiency of seeding. So all these would produce some cost-effective value, as well as decision-making capabilities that would enhance the program at large. So the new space paradigm, I think, has brought a lot of disruption in the space industry. We're seeing this again across many domains, and the concept of smaller satellites that are being deployed as constellations and are powered by the latest technological innovations, taking advantage of cheap launch you see with SpaceX and others in this domain, that access to space has become a lot more economic than it used to be. And then the miniaturization of sensor technology is also playing a role in enabling so many other innovative new entrepreneurs to play a role in this sector, which previously, or even 5 or 10 years ago, wasn't the case. And so what's happening here in terms of these low Earth orbit constellations is that it's accelerating the Earth observation capabilities quite significantly from space. And G42 is in line with those new technology trends in space and is partnering with many of the leading players that acquire data and a wide range of modalities, including optical, SAR, and even hyperspectral. The key is actually the most frequent acquisitions. So the higher temporal and spatial resolution, the better, obviously, so that you have much more data and you're able to draw correlations between and come up with actionable intelligence for the purpose that you're working in. And so in general, our platform is data agnostic. So we're quite, open to many types of data sources or data providers. The commercial players, the usual suspects, obviously the digital globes, planets, and now with the new constellations you have on radar, ISI, and others, as well as with optical sensors like companies like Satellogic. We have relationships with all of them, and we're able to ingest a lot of data into our agnostic and highly intuitive platform that allows for integration with external platforms as well, and also enables on-prem processing if organizations like to utilize the additional proprietary type of data. So it's quite a versatile system, and one that we are continuing to develop and evolve. So if you think about the architecture, this is kind of how it looks, and it's something that we're refining on an ongoing basis. So to me, I think the important thing here is that we engage early with potential partners that want to help us build these systems. The thing that we find that's missing from our team internally is the domain expertise in some of the areas that we feel AI and our technologies can be dedicated to. So what we tend to do is try to find those domain expertise through the companies that we choose to deal with or the government organizations that we choose to support, and have them help us help them, basically. And so this is kind of what we are looking to do with the in support of the UAE's RAIN enhancement program. So in summary, we're a world-class provider of cloud data science and GeoAI services. We have a dedicated cloud computing integrated solution that could be of great support to the UAE RAIN enhancement program. And we're increasing our ability to acquire data that would be very useful to this effort and utilize our supercompute capabilities and capacity to support the program at large. So I'll stop there, and hopefully at the end, I'll be able to address any questions the audience has.
Thank you for your time, Mr. Talal Al-Qaisi, and for such a presentation as well. Now, please join me in inviting Dr. Joe Hatton-Tilla to give a presentation on predicting the susceptibility of mixed-phase clouds to hygroscopic seeding.
Okay, hello everyone. Hopefully you can hear me now. A bit of an issue with the crash in the Zoom application, but okay. I would like to thank the organizers for the opportunity to give this presentation, which is about our work on developing machine learning methods to predict the susceptibility of mixed-phase convective clouds to hygroscopic seeding that occur over the United Arab Emirates region. I would like to acknowledge my co-authors here, and this work was conducted at the Finnish Meteorological Institute as the part of the project OASIS, and Professor Korhonen will give an overview of the project tomorrow. So let's get on with it. So first, a bit of a background. Obviously, the main motivation is the need to identify the occurrence of the clouds most suitable for seeding. And during our project, we have used our idealized cloud visualizing modeling system to study the seeding effects, focusing on summertime convective clouds that occur at the UAE region. And more specifically, we are using a large area simulation model coupled with a highly detailed description of the aerosol and cloud microphysics. And to run the model, as the initial land boundary conditions, we used data from a numerical weather prediction model that was run over the UAE region during the project, as well as then surface measurements of aerosol properties that were deployed by the FMI at the United Arab Emirates in 2018, I think it was. And here in the picture, you can see example profiles of potential temperature and humidity that are sampled from the numerical weather prediction model, and they show a pretty typical structure that we see. So that we have cloud base around 3 kilometers, maybe sometimes a little bit higher, and the cloud top is usually up to something like 8 or 10 kilometers. So they are like these moderately deep convective clouds that we presumably might have successful seeding events. And to facilitate this machine learning approach to predict the occurrence of the most seedable clouds, we need to identify also some indicator variables so that we can tell which clouds are actually most suitable for seeding and which are not. So those are really like the two main things that I will be covering in this presentation. But before I go deeper into those details, I would like to say a few words about our modeling tools. So first of all, the LES modeling was performed by the UCLA LES SALSA model, which is built around the UCLA LES large eddy simulation code that is quite widely used and published by Stevens et al. And the aerosol and cloud microphysical description is given by the SALSA model, which is a bin model, so we can model the evolution of the particle size distributions and track the aerosol properties and cloud processing of the particles. And we have also pretty high emphasis on representing processes like scavenging and this sort of stuff, which are really important for capturing the hygroscopic seeding effects. Another modeling tool that we are using is the TOPAC cloud tracking algorithm that was published by Hagenfeld et al. In the Geoscientific Model Development. And what that does, it basically extracts the cloud mixing ratio and vertical velocity fields from our model and detects and tracks then individual convective cells in the model domain. So what we're simulating is like this cluster of these convective clouds. And here, and for the tracking, we must use quite high frequency output from the model to provide like a robust tracking of the cells. And here in the middle figure, you see actually an example in an XY plane of the trajectories of individual cells identified by the TOPAC algorithm. And then on the right-hand side, there's a snapshot figure where the background colors are given by the column maximum vertical velocity, and then the lines are the outlines of the individual cells identified by the TOPAC algorithm. And using this tool and the data it provides, we can do many sorts of analysis. So for example, here on the left, we have the histogram of the cell lifetimes, and we can see that most of them have a lifetime between 10 and 30 minutes. So they are quite short-lived. Then for the more on the machine learning side of the thing, so our workflow that we have established is as follows. So basically during the project, we have produced this small ensemble of Uclales SALSA simulations of the convective clouds. So most of the ensemble members vary the properties of the background aerosol, and some of them also vary a little bit like the boundary layer conditions and the meteorological conditions, like the boundary layer moisture content, for example. And basically the workflow is that we take that data and then use the TOPAC algorithm to analyze it and identify the individual cells. And for the machine learning, we use the neural network approach, where we need to define input variables and then the output variable, which is the one that we want to predict. And in this case, we basically use the TOPAC trajectories to extract the input and output variables, and the output variable is the seeding indicator that I mentioned earlier. And what is this seeding indicator? So during our project, when we studied this cloud seeding effects in these convective clouds using the Uclales SALSA, we found the results to be like this on the left-hand side figure, which gives you the mean accumulated surface rainfall yield in different sorts of experiments. So the colors are different model configurations. And then the dashed line is the seeding experiment, and the solid line is the corresponding control experiment. So the rain enhancement is then analyzed as the difference between those two for each model configuration. And you can see that the largest enhancement is seen here on the blue and orange lines. And these experiments have a quite high background aerosol concentration. Then for these red and green lines, you get overall more precipitation, but the seeding effect is lower, and these are characterized by lower background aerosol concentrations. So we see that the seeding effect is quite sensitive to this. Then when we dig deeper in these types of like mixed phase convective clouds, most of the overall precipitation comes from the cold precipitation process usually. And analyzing that in conjunction with the seeding effects, we get to this middle figure here, where we have kind of tried to attribute the seeding effects to this cold and warm precipitation process. And if you compare the scales on the y-axis, you can see that actually it seems that the cold precipitation process also pretty much dictates the precipitation enhancement magnitude as well. And looking even deeper, it's coming from the fact that when we do this hygroscopic seeding, even at cloud base, the particles are lifted upwards inside the cloud, and they affect the riming process then pretty directly, which is at the core of the cold precipitation formation process. And when we analyze this in terms of the rime fraction of the ice particles inside the cloud, we see that in these blue and orange experiments where we have high aerosol concentration, the rime fraction is overall like moderate, but we get this increase. The dashed line is again the seeding experiment. We get this increase in the rime fraction due to the seeding. Whereas then when we look at these red and green experiments, the overall rime fraction is higher. So there's less room for the kind of the cold precipitation process to become more efficient. And then we do not see as much of a response to the seeding. So that's kind of the premise that we have been using here so far. So we take the whoops, that's one too far. We take the rime fraction as our initial candidate for the seeding indicator variable. Now I must say that this is not like a fully unambiguous parameter. So it seems to work pretty well when we change the aerosol properties. But then when we change at the same time the meteorological conditions, it's not anymore like a simple one-to-one relationship, but it gets more complex, and there further research is really required. But still, to demonstrate this machine learning methodology that we also have been developing, for now we kind of settled using this rime fraction as the initial candidate. And in more detail, we are using convolutional neural networks because there you can use profile data instead of like individual values to train the networks, and they contain much more information, so that's beneficial. And the training data is obtained from the LES datasets that go through the TOPAC cloud tracking analysis. And the way we sample the input variables, which consist of meteorological observables and the aerosol conditions, we sample those at the onset of each convective cell. And then the output variable, the rime fraction, we sample at the time of a mature stage of the cells, and that we define by analyzing the TOPAC trajectories iteratively and finding out the time of maximum cloud top height for these cells. And here we have then some results from this neural network exercise. So specifically, we have now 10 input variables for the training stage, which cover temperature, wind profiles, and humidity, as well as then the aerosol properties. And here on the top, we have the vertical profiles of rhyme fraction, which are averaged over all of the analyzed cells. And here the blue line is sampled from the model data directly, and the orange line is the prediction given by the trained network. And here on the upper left figure, this is done using the training dataset, and on the upper right figure, it's the same thing, but it uses an independent testing dataset that was not used to train the network. So we can see that on average, these rhyme fraction profiles between the model and the neural network projection agree pretty well, surprisingly well, even though in individual cells there might be and are some discrepancies, but they are kind of averaged away in this kind of analysis. Then on the bottom two panels, it's basically like a similar kind of analysis, but there we take the vertical average rhyme fraction for each of the analyzed cells, and this x-axis just gives the number of cell, basically. So it's just a collection of those different cells, and the x-axis doesn't have any like physical meaning in this case. And we can simply see that using the training dataset, the neural network represents the variability of the rhyme fraction pretty well. And also when using the testing dataset, we capture pretty well the cell-to-cell variability in rhyme fraction, and are able to predict the main features there, even though we are missing some of the extreme values at the moment. But that's probably explained by maybe we didn't cover all of the necessary input variables or something like that. So there's also some work to continue. Now we have to remember that even though, I mean, we find these results to be really encouraging in terms of being able to use this kind of neural network approach to predict the occurrence of cloud suitable for seeding, but we have to remember that these are now based on idealized LES simulations. So it's so far a little bit unclear how well this specific approach would then generalize to more complex and real-world conditions, especially as over the United Arab Emirates, the convective clouds are often driven by the surface topography, and that's something that we cannot very robustly take into account in our current model. Okay, well, I was quite fast. Actually, then I will turn to the conclusions. So basically, we have established a functioning workflow from the LES modeling to tracking the convective cells and bringing that to the machine learning regime. And the convolutional neural networks provide an efficient approach to forecast the seeding indicators in complex settings, at least in terms of the thermodynamics and microphysics. So that looks promising for developing a predictive tool based on information that you could easily obtain from numerical weather prediction modeling or like just your standard observations. And that's a good starting point to work towards like an operationally used tool for identifying these good seeding cases. And as an outlook, well, I mentioned the issue with the rhyme fraction already, so we need some further research in deriving more robust seeding indicator variables. But then there is also the fact that our model is quite heavy to run, so obviously we couldn't have covered the whole parameter space in terms of the input variables. So that needs to be extended somehow in the future to get a more holistic view. And then lastly, which is really important, is the validation of these things and validation of the seeding, how the seeding indicator variable, whatever it ends up to be, how it works and how our neural network predictions work. So for that, I would call for maybe modeling efforts towards more of a numerical weather prediction type of thing, which can be used to make more realistic, specific case studies. And then also because these rain enhancement processes seem to be, at least in these types of clouds, pretty tightly connected to the mixed phase processes, it would be really nice to get some in situ airborne measurements of the mixed phase and ice particle properties in these clouds to validate our model results. So with that, I would like to thank you for your attention.
That was quite the rich presentation. Dr. Juha Tontila, thank you very much for that presentation. And don't worry, we have quite the time to discuss and dive thoroughly and deeply into more details. But for now, allow me, ladies and gentlemen, to invite our third speaker, Professor Eric Frew, who will be giving a presentation on the progress toward autonomous targeted observation and seeding using unmanned aircraft. Let us all welcome the professor.
Thank you very much. It's a pleasure to be here. I'm going to talk about our work on targeted observation and seeding using autonomous unmanned aircraft systems or drones. And I'd just like to acknowledge my collaborators and contributors to this work, as you can see here on this slide. So just a very short overview of the system and kind of what's motivating our project. So currently, when piloted aircraft are doing cloud seeding, the pilot is using mostly visual cues to try to determine what's happening and when to make decisions. The pilot might look at where the cloud base is located, may have some measurements, some radar data of what's going on, look at the cloud tops, and will make a decision, is this the right place? Is this a good place to do cloud seeding? And then, release the material and go from there. The problem with that approach is that there's not a lot of feedback in the moment on the conditions for doing the seeding. And so our project is going to focus on this question of effective targeting, which is one of the more understudied areas in this domain. So the goals of our project are to develop and assess an autonomous unmanned aircraft system that uses in situ data, so data that it's measuring in the environment to decide when to release the cloud seeding material. So you can see here some of the additional technical objectives. We're using some past data to develop some models and some algorithms to predict when cloud seeding will be best. We've been miniaturizing some of our instruments to go on several small unmanned aircraft systems, and then the autonomy of a full system to do this whole process with minimal human intervention. And all of this is combined into a fielded system that we will be deploying in the UAE in this coming summer. So just very quickly here, the system starts at the radar data. So we will use data from weather radar systems that will then inform where one of two aircraft will go. That aircraft will be performing the in situ sensing using miniaturized sensors that it carries in the environment to sense and to predict when the conditions will be appropriate for cloud seeding. That will then call in a second unmanned aircraft system that carries a seeding material and will release the material in the appropriate regions. And all of this will be done with minimal human intervention. The goal is to make this fully autonomous with a human operator just observing what's happening and paying attention. And then we will be assessing this system through a field campaign this coming summer. So first, I want to talk about the aircraft itself and the sensors that we're carrying. So the key to making this whole system work are the miniaturized sensors to give us the insight into what's happening in the clouds and in the environment. And so you can see here kind of on the bench, the three main miniaturized sensors that we'll be using: a printed optical particle spectrometer, a multi-angle inertial probe, and then a cloud droplet probe. And then you can see the supervisory computer that pulls all this data together. As part of this project, that cloud droplet probe was miniaturized by our colleagues at Droplet Measurement Technologies. They miniaturized the housing and reduced the weight so that it's appropriate for small unmanned aircraft systems. We worked with the vendor to create an inlet for our printed optical particle spectrometer. And then you can see here the electronics and the board to bring all this data together and to provide it to an autonomous algorithm on board the aircraft, while also providing insight to the human operators that are located on the ground. All of these will go into an unmanned aircraft system. We've been developing something at the University of Colorado called the Super Raven. Raven's an acronym. I forget what it stands for, but basically we have a robust and endurant unmanned aircraft system. You can see in these images sort of the scale of this aircraft. It has a wingspan of just under 5 meters. Target endurance carrying the sensors or the seating material for this project of about 3.5 hours. The range itself for this project is actually limited by communication. So we will be staying within 10 miles of the operating system because we need to be able to communicate to the aircraft at all times, though it could probably extend a bit further. Another key feature of this aircraft is it's made out of highly durable foam, so it's a very rugged system. When we're deploying this system in the mountains in the UAE, it's going to be landing in gravel, rocky roads, et cetera. So we really need a system that is reliable enough to be deployed every single day. You'll notice that there's no landing gear on this aircraft. It takes off through a catapult, which you'll see a video here in a minute. And it just lands wherever it needs to by skidding on its belly. And again, that foam protects it and makes for a robust system that we can use multiple times in a given day, multiple days over the course of weeks or months long campaigns. We're also building a second aircraft that's carrying the seating material. For this project, we're not carrying a large amount of material, but we are carrying enough material to demonstrate the ability to seed in the clouds in the regions that we identify. So you can see here a schematic for the other aircraft. It will be carrying several containers of seeding material so that it can launch multiple times if needed, or it can launch all the material at once. And then this here is, again, a video of that system. You can see it's a bungee launch, makes for a fairly quick setup, quick launch. You can do that pretty much anywhere. You bring the stand, set it up. We can launch it. Takes us between 10 to 30 minutes to do the full preparation to then deploy the system. And the key here is when we're trying to deploy into the weather, into conditions where you don't know in advance where you're going to be and what's happening, that speed of launch is part of what makes for a successful mission. So I'll next describe the autonomy architecture, really the fundamental aspects of this project, excuse me. Overall, our autonomy architecture really has a dispersed framework where we have autonomy based on components at 3 different locations. So on the far right of the image here on the screen, you can see the aircraft itself. So on board the aircraft, we have the autopilot, the basic flight control of this system, and then we have a supervisory computer, which is taking in commands and running some of the logic of the system. It's running all the sensors, that cloud seeding algorithm, for example. But the majority of the intelligence happens at the field site. So this is going to be what we often think of as the ground station where the pilot sits. So the operator station or the field site will be no more than 10 miles away from the aircraft. We will always have that green communication link from the field site to the unmanned aircraft itself. And a lot of the flight planning, the trajectory design for the aircraft happens at the field site. And then that presents the information to a human operator who can approve the operation or not. That's just something that we've built in for this particular campaign, though in practice, that could be a completely automated process. You don't have to have a human operator involved, but for this campaign, that will be the scenario. The reason why we are doing the autonomy on the ground is because the algorithms are also interacting with the data from the weather radar site. And so we're doing some weather processing, which I'll describe in a moment, which sends tracked information to that field site, which then does the remaining trajectory optimization or the remaining autonomous design. This is a schematic of a mission profile. The main thing I want to point out without going through this whole diagram is only one piece of information is needed sort of in advance of the mission, and that is an approximation of the lifted condensation level. We need to have some awareness of what altitude we're aiming for, where we expect to start the seeding. So once that's given to the aircraft from soundings at the beginning of the day or at the beginning of the mission, the rest of the mission is autonomous. And so this just shows some of the flow in terms of the aircraft taking off, getting to altitude, heading to a target region. We call these regions of interest, or the polygons as referred to here. I'll say more about that in a moment. And again, the aircraft launches. We have a cloud seeding probability algorithm that's running online while the aircraft is in flight. Aircraft makes some decisions on its own on whether or not to release the material, do the measurements of what the material has done, or to continue surveying until conditions are found that are appropriate. So in that architecture that I described, those 3 layers, the first or three locations where things are happening. The first location was the weather radar system, and so at the weather radar system, or connected to the weather radar data, we will be running Titan LROS. This is a package that does storm tracking for us, and so that package actually looks at the radar reflectivity data and is able to track the condensation or track the moisture in the air and predict where these clouds and where these formations or where these storms, these convective regions are going. And so that system will be running and will be tracking potential sites for the aircraft to sample. So the outcome of this is something that we refer to as a region of interest. Think of these as a set of polygons for the unmanned aircraft system to go explore that are likely to have regions of good seeding. In order to communicate from the weather radar system or from the system that's running in Titan LROS, we've created an XML schema that can, send data over the internet to the field site with the location of one or more of these regions of interest for the unmanned aircraft to sample. That data is then handed over to the trajectory design or the autonomy design work for the aircraft trajectories at the field site. So the aircraft is being commanded to explore these regions of interest, as we call them. And so we've designed several different search patterns to explore these regions, a standard raster scan, spiraling into, spiraling out of the pattern, or even cutting across diagonally on this. And all these patterns can be put in the moving frame of reference of the storm. So as we've identified the regions relative to the storm to sample, this pattern will actually shift with the storm so that we are efficient in how we're covering the regions themselves that are most appropriate to produce the cloud seeding. So this is another video that will sort of showcase the components here put together. So in this particular video, that shaded blue region is meant to represent one of these polygons that would be delivered from the Titan LROS system to the field site. And then there's a dashboard here. This is what the human operator and the science operator would be observing while the mission is happening. And so you can see that the operator has the ability to indicate different types of behaviors, different preferences, for example. These are all issuing commands to the aircraft, although a lot of this, the mission itself is automated. We're able to have the operator determine which type of scanning pattern, for example, the aircraft will follow. So you see here the raster scan pattern, for example. We could ask the system to replace that using a different pattern. Here, the aircraft is going back and doing that pattern again. I think I'll let it play for just another minute longer. It's going to do one of the spiraling patterns, for example. And so you can just see all of this is automated. There is an operator that's able to issue commands as well. That's done mainly to increase the potential science return. If the science operator wants to try something differently, they may intervene. It's also there to satisfy the safety regulations where the human operator is always able to take over and bring the aircraft into a safe configuration if there's a need to do that in response to other situations in the environment. So this particular picture here just shows a little bit more messy how we implement the actual autonomy that pulls this all together. So this is a state flow diagram that actually describes the software that produces the autonomy on the ground station. And I won't go through all of this, but you can see a variety of different modes or tasks if you wish to think about them that way. The safety task is really the aircraft is just in a sort of loiter pattern waiting for a command. The aircraft, the typical concept of operations will actually be to launch this aircraft, to get it into the environment near where we expect the storms to be located, and then to be in this wait or loiter pattern until those storms are coming from the Titan LROS system. And then you can just see some of the logic in terms of searching the region. If the cloud seeding probability is high enough, enter a seeding mode, the profiling mode to generate some additional information about the environment, and then the seeding evaluation mode after the seeding material has been deployed to return to that region and try to and take measurements to record the effect of the seeding itself. And so this is kind of the way the software is implemented. The autonomy is implemented on the ground station that sends the commands up to the aircraft. So the next thing I want to talk about is that cloud seeding probability algorithm that I described. So, the heart of all this autonomy is getting to a region where we believe cloud seeding will be effective. In order to assess that, we have a cloud seeding probability algorithm. This is based on warm cloud precipitation microphysics. We essentially run a parcel model looking at droplet activation. It's based on the lifted condensation level, the updraft velocity, and the concentration of CCN. We essentially propagate or predict the time to drizzle both with and without seeding, and look at the difference in those predicted times. And that is directly related to the probability of seeding. And then we have essentially a three-dimensional phase diagram, if you will, of high and low probability of seeding in the environment. And so based on that, we can set a threshold. In our case, we look for a probability of 50% or more, which will then tell us to activate the seeding material. Interestingly, depending on the temperature, the cloud seeding probabilities vary in their dependence, say, on the updraft velocity. So you can just see here two examples. The figure on the lower left, that is the cloud seeding probability for warm temperatures. And there, the probability is higher as the updraft is higher. That's the y-axis on that plot. Whereas on the right-hand side, for cold LCL temperatures, higher probability is associated with a lower updraft velocity. The material spends more time in the environment. And so this is essentially a three-dimensional phase diagram, if you will, of probability. And we track the in situ conditions. And once we are above 50% for a long enough time, we'll declare that high probability and we'll initiate the seeding activity. We do have this is a dashboard that we provide to the science operator on the ground to track what's happening. I'll actually play a video and sort of talk through it here. This is a simulation of our system using some data from Murakami flight in 2017. You can see the main window there shows you the flight path of the aircraft. That dashed line is meant to represent one of those regions of interest. On the far right, you can see that phase diagram. This one is for the specific LCL temperature. And you can see that sort of circle icon indicating the probabilities. As we entered the region of interest and the probability went higher, you saw the orange star. We then released the material or simulated the release of the material here during the flight path. The circles, the black circles also represent when the aircraft would go into the clouds or not. So we're able to track all of this information live, provide it to the science operator, to the human operators while the mission is happening. But I want to stress that the system is making all the decisions, where to go, when to seed. This is just providing us with insight into what's happening so the science team can validate the autonomous system is behaving as expected. So lastly, I'll just comment on the field campaign that's coming up. We had a field campaign scheduled for this past summer, but obviously with the events of the global pandemic, that was postponed. We expect to participate in a field campaign this coming summer 2021. In terms of designing our field campaign, we're really balancing three major factors. The first is the weather. Obviously, we need to get to the conditions. Secondly, are the aviation regulations. And then lastly, conditions on the ground to provide an operating center for us. So we've decided to work fully out of the Fujairah air traffic domain to simplify the coordination there. And you can see, I hope you can see this light blue circle. That is our operational area. We're limited to about a 10-mile radius from the ground station. And so that leads us to that circle there. So again, we'll be spending a month in the UAE this coming summer to fully validate our system and to demonstrate the capabilities here. So that really concludes my presentation. I'll just summarize by saying, we have this autonomous system that can do targeted observation and seeding. There will be a human operator can interact with the system, but everything is capable of behaving fully autonomously. We're refining that concept of operations. We're refining the implementation of the cloud seeding documentation, some final tweaks to our aviation authorities, and then we will be developing that second aircraft, finishing the flight worthiness certification of that second aircraft in preparation for our field campaign. So with that, thank you very much for your time.
Special thanks to Professor Eric Frew on this presentation. And for now, we will be welcoming our fourth speaker, Dr. Duncan Axis, who will be presenting on the intelligent systems in rain enhancement technology. We welcome him as well.
Hello, everybody. My name is Duncan, and I will be speaking about intelligent systems in rain enhancement technology. Artificial intelligence is one of the hottest topics today and is rapidly disrupting various sectors, including operational meteorology. In this presentation, we consider the programmatic aspects underlying development of intelligent systems in rain enhancement activities. This is done by introducing a design concept for an intelligent system and highlighting one simple example of its implementation. What you see here is a maturity curve for an intelligent system. The field of intelligent systems focuses on how machines interact with human users in a changing and dynamic environment. Rainfall enhancement technology can fall anywhere on the maturity curve that you see here, depending on the value that is being extracted from the AI. So let's explore this one level at a time. At the lowest level, L1, cloud seeding is being done by intuition with no guidance from sensor data. This is the level at which most cloud seeding programs operate. They typically execute seeding operation based on rules of thumb. For example, looking at the cloud system and trying to understand where the updraft might be or where the supercooled water might be in real time. The level up is level 2, and this is seeding that is being done with what I call dark data. This means that the seeding device, the seeding aircraft or a cloud seeding generator, has instruments, it's instrumented, but the data is not readily available or actionable in real time. Work at this level establishes a clear data collection process and identifies the value of specific insights that these data can generate. However, the value from AI is quite low. The next level, level 3, is where the seeding is being done with different data elements leading to insights. This means that the seeding device is instrumented, so the aircraft or the cloud seeding generator would have instruments on it, and the data is readily available in real time for the human to act on it. The seeding done at this level requires human intervention. However, the key factor that differentiates an L3 system from an L2 system is that the value from AI can drive decisions to conduct seeding. These real-time data-driven decisions could range from where and when to seed, the method of seeding, or how much seeding material to release. The highest level would be level 4, and this is consistent with what Professor Eric Frew was describing. This is seeding that is done autonomously based on insights from a sensor system on board the seeding device. It's done without human intervention, it's autonomous, and it requires a fairly advanced level of AI leading to completely autonomous solutions. An example of this is a system that accurately interprets sensor data, maps the environment, and processes a wide range of variables to make decisions like a human. Next in my talk, I will address the how. How do we go about designing an intelligent system? To answer this question, I will introduce the design framework for an intelligent system. This system advances the concept beyond seeding by intuition. Specifically, this system incorporates real-time observational data with simple models to produce insight towards a seeding action. In this case, a high level of innovation is required to advance the system from L3 to L4. One major component of the design framework applies existing knowledge or data or training data, hypotheses, and algorithms. The key property for a prototype system is that the algorithm lives on board the seeding device, and that is easily tunable through training data. The algorithm feeds into a classification method on board a real-time sensor system that collects relevant data that are attributes to cloud seedability. Seedability meaning how seedable the cloud is. The classifier calculates seedability through thresholding, decision tree, neural network, or other classification methods. The difference between an L3 and L4 system is autonomy. L4 system could be similar in concept to Professor Fru's third cycle award. Ultimately, the intelligent system process ends with a seed or no seed action. An important post-processing step is evaluation. In this step, the focus is on quality improvement through data analysis and interpretation. This step leads to a refinement in the algorithm and better performance of the system as a whole. One major component in the design process is forming a hypothesis on the seeding. This hypothesis is based on assumptions that complex cloud microphysical processes proceed in a predefined and exact path. For example, when cloud seeding aircraft insert seeding material at cloud top, the hypothesis relies on the assumptions that the seeding agent will cause supercooled liquid droplets to be converted to ice crystals. Therefore, the presence of supercooled liquid water must be confirmed prior to seeding. When seeding at cloud base, it is assumed that sufficient updraft is present to carry the material to the area within the cloud where supercooled droplets are present, where it can be effective. Therefore, the presence of sufficient updraft must be confirmed. Once a hypothesis is formulated, it must be tested by observations and experiments. This slide highlights a hygroscopic seeding experiment conducted in Texas in the summer of 2005. The hypothesis here was that seeding of continental convective clouds with salt micropowder accelerates warm rain. What was unique about this experiment is that when the seeding material was released from the aircraft, an atmospheric tracer was also released along with it. This allowed for the unambiguous identification of seed volumes within clouds. That means there was no confusion whatsoever whether the volume of the cloud was seeded or not. The results indicate clearly that a seeding signature was observed as additional drops in the tail end of the drop size distribution, or the tail effect, as can be seen by the plot of the drop size distribution on the right compared to that adjacent to it. The figure on the right shows drops greater than 30 microns in the seeded area that are higher in number concentration compared to those in the unseeded area. This result was consistent with previous studies. For example, the work by Mater et al., where seeding was observed by broadening of the drop size distribution compared to the surrounding area. However, not all clouds are expected to respond in the same manner because the microphysics is different. This is where it becomes difficult to develop an intelligent system, because the process of identifying seedability must be described. We do know that cloud seedability is a function of cloud-based temperature, cloud top temperature, number and size of the pre-existing cloud condensation nuclei, parameters of the drop size distribution, and the concentration of ice particles. At a minimum, an intelligent system should incorporate sensors that measure some of these parameters. With this in mind, as well as emphasizing the need for a simple and highly deployable system, the CWIP was developed. So CWIP is an instrument, and the acronym stands for Cloud Water Inertia Probe. And it is an example of an L3 intelligent system. It utilizes technology of high operational readiness available in real time to assist the cloud seeding pilot with making seeding decisions. Development of the system started in 2011, and in the figure in the left, you see a sketch of the concept for the display that I put together that would show the pilot the needed information. From that concept, today, CWIP is a fully operational system of integrated sensors, and it is installed on 12 aircraft to date. The CWIP sensor data include temperature, updraft velocity, liquid water content, and relative humidity. These data are passed through a classifier, as shown in the schematic, with a simple rule-based model. For example, if the updraft and liquid water content exceed a certain threshold, The seed score, which is the indicator for seedability and is visible to the pilot, indicates the area that is more seedable by the value of that seed score. The pilot can readily observe the seed score and act accordingly. Here we see example data from an aircraft conducting seeding at cloud base. The time series are shown in this playback interface. So the time series on the top, time series 1, shows altitude and ambient temperature. Below that, we have liquid water content and relative humidity, then the vertical velocity, and at the very bottom is the seed score that indicates seedability. In the first part of the time series shown in red, the aircraft is flying at a temperature of 8 degrees C with liquid water content up to 1 gram and an updraft in excess of 2 meters per second. This is conducive to good seedability, as indicated by the bottom time series, where the seed score shows an elevated score compared to the surrounding area. So the region of higher seedability is being identified. What we see here is also a dashboard that would be available to a meteorologist sitting on the ground, guiding the operation, having data access in real time. Future work would include the addition of data elements to improve the seeding metric. A concept to improve a determination of cloud seedability is to combine the drop size distribution from the cloud droplet probe, for example, with a simple droplet coalescence model. The figure on the left shows a measured size distribution in solid green that is modified for a seeding effect. It is being modified in 2 different ways, one simulating a competition effect and another one simulating a tail effect. The plot in the middle shows how the model calculates coalescence for the measured size distribution, and the plot on the right shows how the model calculates coalescence for the measured size distribution that is modified for the tail effect. And in this plot, we see that there are additional drops in the drop size distribution in the tail end for drops greater than 30 micron compared to the one where the model proceeded with the calculation without modifying the size distribution. This suggests that the measured size distribution would react positively if seeded, and this can be done in real time. So this is an example of future work that can be done to add data elements to the L3 autonomous system. In summary, there is a body of good work in research related to rainfall enhancement. These include new observational tools and models. However, new technology applications and innovation is required for these to benefit the operational community. There is a need to transition from dark data to data that leads to insight. This improves the success of seeding missions, and it requires dedicated focus and programs. This type of development can help guide the research and accelerate the maturity of intelligent systems, which increases the value of AI. Once we demonstrate that an L4 intelligent system, meaning a fully autonomous system with limited human input, once we demonstrate this is feasible, we will create a shift in the way we conduct rainfall enhancement in the future. Thank you very much.
Our thanks to Dr. Duncan Axsa. Now, ladies and gentlemen, you've met our speakers. Let us now invite our distinguished speakers from the session to exchange their knowledge and ideas. And I also invite Dr. Yousef Wehbi to moderate this panel. One small keynote to our speakers as this panel discussion is beginning. In order for your microphones not to intervene or interrupt another speaker, make sure you place them on mute before you relay your message. The floor is yours, Dr. Yousef Wehbi and everyone else.
Welcome, everyone. Thank you to our MC and all our speakers so far. Good morning, afternoon, evening, depending on where you're joining us today to attend this exciting and futuristic panel, I must say, to close our forum's first day agenda. I want to remind the audience to please use the chat box at any time to send in your questions. So building on the insightful presentations given by our 4 distinguished speakers so far, they'll be joining me to discuss the value of leveraging high-performance computing, AI analytics, and UAVs to advance rainfall enhancement research in general, and more specifically, cloud seeding operations. Again, our distinguished panelists include Mr. Talal Kaisi, Vice President of Strategic Projects and Space Program at Group 42, welcome. Professor Eric Frew from the University of Colorado Boulder, as well as Dr. Duncan Axisa, Director of Science Programs at Droplet Measurement Technologies, also from Colorado. And finally, Dr. Juha Tantila, a scientist from the Finnish Meteorological Institute. First off, I'd like to thank Mr. Talal for his insightful presentation on all the activities being done at G42 here in Abu Dhabi. And I'd like to start off with the first question for you, Mr. Talal. We all know that AI has been widely used in the post-processing and calibration of output from physics-based climate weather prediction models. But some argue that beyond post-processing, we've seen a lot of attempts that want to replace the physical parameterizations altogether and move into more AI-exclusive forecasts. So my question is, do you see the concept of exclusive AI-based climate or weather forecasting taking shape over the next 10 years? Or is a hybrid approach where we'd combine sort of the physics and the AI the most promising path for that?
Yeah, no, thank you for your question, Yusuf. I think it's a very important one. Not one I'm particularly the most qualified person to answer, but from the limited exposure I've had in this domain recently, I think a stepped approach and a sequential one at best would be needed. So, be it a hybrid initially, and then a more AI-driven one. The key with AI support of this type of an initiative would be the scalability. And I think we can get to that point quite quickly. And that scalability would allow for a lot more types of intelligence to be drawn out of the data that's ingested. So the more granular the data, the higher resolution the data, the better in terms of the predictive modeling, a supercomputer would be able to then support generating analytics for. So I think we're not totally there yet when it would be an exclusive AI type system. I think there is always in the near term going to need to be that human factor that supports and drives the generated outcome. But in the future, I think it's quite inevitable that the scalability of high performance computing would allow for predictive modeling to be done in a more automated fashion than is the case at the present time.
Yep, indeed, Mr. Talal. And we did hear the term data hungry a lot when one of the previous panels. So of course, that's a precursor, important precursor of making a decision on this. Right. My next question will go to Professor Eric. Thanks a lot for your presentation, giving us an update on the project, on the exciting use of UAVs. Besides the socioeconomic and environmental savings that are promised with the use of UAVs for, say, cloud seeding operations, one issue that comes to our minds is, are we there yet? So is current UAV technology capable of operating in severe weather conditions and storm conditions, which we usually target in our cloud seeding operations? So we're already in a turbulent environment. So could you maybe give us your take on this?
Yeah, thanks a lot. It's a pleasure to be here. I think, well, yes, I think the technology is here. I think that the fundamental limitation really over the last decade, we'll say, has been the logistics and the regulations and having those catch up with the technology so that we can really deploy systems in these environments at a regular enough pace to really refine the systems. I think the technology is there for teams who are practiced with it and are skilled to deploy in these extreme environments. The technology is perhaps not there where you would simply purchase a system on the shelf for these types of extreme environments. But I do think that the unmanned system technology, the drone technology, is reliable. as with manned aviation, it's taken a long time to really refine our systems to the level of safety that we really want to see. And I think with drones, we can easily get there once we get these experiences and get the practice sort of under our belt. But I'm very confident that these systems are safe and robust and can operate as intended in these environments.
Thank you, Professor Eric. That sums it up pretty nicely. I'll move to your co-PI, actually, Dr. Duncan now. I personally know, and of course, many of those who are watching us today, that you were involved in many operational cloud seeding activities around the world, campaigns and field programs. So I'd like to ask you, based on your experience, do you think conventional cloud seeding flares should be replaced with maybe new delivery mechanisms that are more compatible with UAV systems, say like in Professor Refru's project, with their aerodynamics and the payload limitations we have in these emerging delivery mechanisms? And of course, seeding material release rates and concentrations are key in the question. Perhaps you could share some insights on this from previous experience and as you're learning through your project with Professor Eric, of course.
Yes, Dr. Youssef, thank you for that question. It is indeed a very important one. I think when it comes to seeding agents, there is no one size fits all. And this is because the hypothesis on which cloud seeding operates is that we are trying to introduce an engineered aerosol that in its concept operates based on the premise that it would be effective having knowledge of the pre-existing aerosol concentration, the pre-existing CCN number concentration and size, and the pre-existing ice nuclei concentration that is impacting the clouds. So engineering a flare or a seeding agent has to be done in the context of the environment of its intended release. I think that's a very important point. Secondly, the way it's packaged then would depend on the vehicle that is being used for its release. Traditionally, we have been using flares that are packaged in a tube because they are easily handled. They can resist deterioration because they are not prone to leaking moisture that would change the hygroscopic properties. And they are very operationally ready for deployment. That doesn't mean that we should use them widely without prior knowledge of this pre-existing CCN and IN knowledge of whether the material would be effective. In terms of seeding rates and also seeding material, some of the work that I did previously showed unambiguously, without any doubt, because we were able to put a tracer in the atmosphere and define precisely the seeding volume using a chemical tracer, that cloud seeding is effective when you release very large amounts of seeding material. So a very large rate was required. And this would depend again in the environment, but in the environment that we were operating in, which was convective clouds, we needed to release very high rates because the material disperses very rapidly within the cloud volume. So we have to really be cognizant about the environment in which we're releasing the material. Also, how the material is packaged is extremely important. And then identifying seeded volumes versus those that are not seeded in a very precise manner is very important to determine whether that material is effective.
That sums it up excellently. I couldn't have asked for a better answer. Thanks, Dr. Duncan. I'll now move to Dr. Juha. You shared a lot with us on the AI-based tracking of the clouds, etc. My question to you is more on the cloud microphysics. I know you're also working on that pretty closely with the FMI team. So as we all know, cloud microphysics refers to the small-scale, sub-micron, computationally expensive processes that affect cloud and precipitation particles. Current microphysical parameterizations primarily rely on just two parameters, and that are the mass and the concentration of cloud droplet in our droplet population. So we call it generally a two-moment scheme. So my question is, how can we leverage machine learning to be able to reach higher order schemes and replicate more closely what's happening in the microphysical processes? So my question is, how do we reach maybe 3 or 4 or even 6 order schemes leveraging machine learning? And again, in my mind is that gap where we need the observations. It's a data hungry process. So how do you maybe align those two challenges together?
Yeah, I think this is kind of related to the previous discussion on your earlier question about should we like replace parameterizations with the AI methods totally, or go with something intermediate? Then I would go with the latter. So basically, we would then have physical schemes based on like fairly simple first principles, but we could use like machine learning methods to bring in some of those additional details that we, for the foreseeable future, we don't have really like a way to directly calculate because of the computational limitations. So in that sense, that would be probably the way to go with that. And of course, yeah, I mean, probably the availability of the observations is a quite, I would say, even a limiting factor there. So that's something that would need to be increased to make that happen, I would say.
All right, I'm just going to throw a keyword out there that I've been hearing a lot nowadays. It's about CubeSats. Maybe Mr. Thal can allude to that in the later part of the discussion. I think those are being used in a lot of fields, and they're quite relevant for gathering those in-cloud measurements. They're so precious to our models in the microphysical processes that we want to simulate here. Back to you, maybe Mr. Talal, navigating back to some points I raised before. A lot argue that when we go with machine learning algorithms to sort of resolve the physical processes, we might violate these physical laws in the sense that mass or energy conservation, or even we may fail to construct unseen conditions such as extreme weather events in this specific context we're discussing in the forum. But this is also a general question for all applications which AI and machine learning is being used for. So that said, there's always this black box stigma that's associated with AI, and a lot of research is now going into explainable artificial intelligence. So my question is G42 attempting or planning to help whiten this black box stigma that's associated with AI, or maybe you could share some future plans if that's not already being done?
Sure. Yeah. No. Very much so, Yusuf. I think as I explained in my presentation, we have the Inception Institute of Artificial Intelligence that's always looking at the cutting edge fundamental research, and now we're looking at ways that we could translate that into commercialization and applicability. And this is a key pain point, obviously, in trying to sell, quote unquote, the benefits of employing these types of methods to big and hard problems. And you're right. I mean, there are certain blind spots and black boxes at the moment, especially when you can't really kind of think of every single different scenario. But that's where the simulations come in. That's where the amount of data and time that goes by will improve and iterate on those processes to get them to where they're more optimized and can support the various use cases that we look at. In fact, one of the questions that you asked Dr. Duncan is a very interesting example here. If you're looking at different types of materials that could be used or substances for seeding operations, there's no better way to do some novel material research than going through a large number of simulations and exploring the efficiency. And you can only do that effectively and at scale with thousands of parallel cores. And that's where kind of, having the cloud compute infrastructure as well as our HPC provides the ideal environment for such experiments.
Indeed, indeed. Before I move to the audience questions, I'd like to check if any of the panelists has anything to add maybe on what we've discussed so far. Please go ahead. Feel free. All right. I'll move to the first audience question addressed to, I'll keep this addressed maybe to Dr. Duncan and Mr. Talal. Feel free, whoever wants to go first on this. It came from Professor Martin Umbum from the University of Reading, the UK. He says that AI solves data problems, but are the problems related to data processing or related to physical understanding when it comes to cloud seeding operations? Maybe Dr. Duncan, you want to go first on this since you're more experienced with the cloud seeding field in general?
Sure. I think going back to the very first slide that I showed of this AI maturity curve, when it comes to rainfall enhancement operations, we are not making good use of data. So the data is dark, it's there, but it's not made available to the operator. We have very good models that are predicting areas where to seed, for example, maybe a couple days in advance. Or we have highly instrumented aircraft and very capable radars and other remote sensing capabilities. These data are dark to the operator that is conducting the operations. Yes, we have a meteorologist that is assisting and talking to the pilot. There is a time lag of communication and the time lag of information there. So we can do better, actually. And this is why we need to put a program in place to make these data more accessible, where they provide insight to the operator, which could be the person on the ground or the person doing the operation, so that they can act on it. So that now elevates the level of an intelligent system from this L2 to L3 level, where you have data that is immediately actionable. And in order to move now to autonomy, which is the L4 system and what Professor Eric Frew is working on, then that data has to have a higher level of AI. But we are so stuck in this dark data phase and focusing a lot of our research on improving these tools. Yes, it's good to improve these tools, but they can't remain dark to the operator.
Indeed, thank you, Dr. Duncan. Mr. Talal, would you like to add anything on this?
Yeah, as you rightfully mentioned, Dr. Duncan's a lot more well-versed in this area than I am, but I did pick up on a couple of points he made that I think might be something that I could chime in on. So, Dr. Duncan mentioned time lags, and I think one of the things that I believe, at least with what you mentioned, Yusuf, earlier in terms of CubeSats, is that we are going to have the level of density in low Earth orbit with CubeSats because of the new accessibility to space that, both low-cost launch as well as miniaturized technologies and more of a plethora of companies realizing the benefit of creating low Earth orbit constellations is going to have. And that, in effect, is going to increase the revisit times, where you'll get near real-time data to then induce the accessibility of actionable insights. So I think that's one area where you have to have both sets, the hardware and then on the AI side, the ability to make sense of that in near real time to produce actionable insights for an operator to be able to conclude certain decision-making operations with.
Indeed. My next question, and maybe the final one, because we have a little bit over time. I don't want to keep everyone. I know it's just morning now in the US. So My final question came from Dr. Rudolf Prinches from NCAR, National Center for Atmospheric Research in Boulder, Colorado. And he was asking Dr. Juha, how do you treat ice formation in the model based on the Rhine growth being so important in the seeding, as you noted?
Yes, so our modeling approach for the ice basically follows the same idea what is behind the P3 microphysical scheme, if you're familiar with that. So basically we have separate tracers for unrhymed and rhymed ice because they can be separated in terms of the processes that create them. And for ice formation, we use like these parameterizations based on the classical nucleation theory. So that part is pretty simple. But then we have these separate mass tracers for the different types of ice within the size bins for the ice particles. So we can then get the mass fractions for the different particle types.
All right. Well, I'd like to thank all our panelists today for making the time to join this interesting session. I see a lot of diverse backgrounds, and it's definitely the way forward to improve the field of weather modification in general. I just want to urge everyone to attend tomorrow's session to dive deeper into the innovations in weather modification research and where it stands within the bigger picture of climate change. Again, thank you to everyone who participated today, and of course, our distinguished panelists that joined me in this session. Thank you very much, everyone.
Thank you.
Thank you.
Thank you for Mr. Yusuf Wabi and for all of our panelists, as well as every speaker who joined us today in this promising forum. Thank you for joining us today, and we would like to note that if anyone has missed any of today's sessions, then they can watch all of IREF sessions on www.iref.ae. We look forward to welcoming you tomorrow for the second day of the 5th International Rain Enhancement Forum, which will commence at 3 p.m. UAE timing. My name is Yusuf Abdul Bari, and it has been my pleasure to be the host of today's forum. Thank you very much, and stay safe.